Okay, so the first day I presented Scratch was one of these persons that stood with us for 12 years. Here's another Scratch person. Noah has been always on with us. He has an amazing career in NLP, of course, by this time. Yes, and that's some of the appointments that we probably dispelled, so I'm just going to pick two. He's a professor at the University of Washington in Seattle, and he's also a research manager at the AI Institute. He also has a large career going to the CNU, as a professor, then PhD in Hopkins, and has served in a lot of committees. So, the person of amazing experience, great insight as well, and very, very much looking forward to this. So,
thank you. Thanks so much. Thanks for the introduction. I hope they put that on my tombstone when I die. He served on lots of committees. That's a very fitting thing for an academic. Okay, so I am delighted to be back with the Lisbon Machine Learning Summer School in person. I haven't missed one yet, although, of course, the past couple of years we've been doing this on Zoom. This is going to be way more fun. So what I'm going to talk to you about today is sequence models, and I'm going to give you a very specific take on sequence models. This is probably the one awesome thing about this lecture. I always start by saying this is that I don't have to change anything because the material that I'm teaching you, it's a relatively self-contained topic that was more or less figured out by the 1960s, 1970s. So long before I was born, probably before any of us were born, the ideas that I'm presenting you were worked out. And so you may think, wow, why are we learning this ancient, oh, you're right. I have to turn on the.
Yeah.
All right. Should I start at the beginning again? Hi, tombstone, blah, 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 blah. All right, we're back. So this topic was settled more or less in the 60s and 70s. And so even the most technical things I'm going to show you are ideas that were resolved a long time back. But it's still, but I think it's important actually to understand. I was thinking about this morning. Why do we still teach this old stuff? Hopefully you'll agree at the end of the lecture. I think understanding some of these ideas will help you in the future if you deal with anything structured, which you will if you work with language. But also, you hear people say, like Hannah said yesterday in her lecture, that one of the challenges of machine learning and NLP and other areas of AI these days is that we deal with these black boxes. We don't understand what's going on inside the models. And it occurred to me that a lot of people who've only known this sort of deep learning world might not understand what we mean when we say that. So this lecture is going to give you some modeling tools that contrast very sharply with that black box feel. So you're going to get to see what you're giving up when you go to an end-to-end deep learning approach. And I'm not opposed to using deep learning. I'm not opposed to end-to-end approaches, but I think it's really important to understand the different ways you can do things and how they relate to each other. And the only way to do that is to see something that contrasts. So hopefully you'll enjoy this. We're going to start off with some really classic tools called Markov Models, and then we'll get to kind of the heart of the lecture, which is a model called the hidden Markov model. Why it's hidden, that will be revealed. The algorithmic focus of the lecture, the one thing you're going to remember, hopefully, if you take away one algorithmic idea, it's the Viterbi algorithm. Who knows the Viterbi algorithm already? Awesome. You're going to learn it again. And I don't know if you're like me, maybe the world has gotten simpler, but it took me like 2 or 3 times before it made sense. So hopefully this will be the time that kicks you over the edge and it'll be even better. And then I'll talk about some other inference algorithms for HMMs, because the cool thing about models like HMMs is you can ask more than one question. They don't just do inputs to outputs. They're generative models that you can do a lot of things with. And then finally, we'll put the learning part at the end because the learning part builds heavily on the other parts. Okay, so Markup models. One very simplistic view of text that I think is fairly pervasive now that we're in the deep learning ecosystem along with every other kind of AI. Is that text is basically just a sequence of symbols, and we can do this at the level where symbols are bytes or letters or things like word pieces or words. I'm going to be very abstract about this today. Most of the time, I'll let sigma be the set of symbols following from theory of computation. If you need to be concrete, think about it as a word, or each element of sigma is a word. And what we're going to be modeling here are going to be sequences of symbols. So we use sigma star to denote the set of all sequences of any length of symbols in sigma, and that should be obvious. It should be it's an infinitely large set. So we're trying to talk today about building probability distributions over these infinitely large sets of sequences. All right. Am I talking about generative models or discriminative models right now? That's the first pop quiz in the lecture. Does anybody raise your hand if the question makes no sense? Okay, so raise your hand if you think I'm talking about generative models. A few tentative, maybe 10 hands. And who thinks I'm talking about discriminative models? A couple people. Okay, but the majority said generative and the majority was correct. So, kind of a high level machine learning concept, hopefully review. When we start talking about probability distributions or telling a story about our data, about the origins of our data, like a myth, like the story of Christmas or something like that, then we're probably wearing a generative hat. We're probably talking about generative models. When we start talking about just sort of sorting things, we get inputs, we give labels, and the model is essentially, it exists only to do this one sort of job, to discriminate class A from class B, or whatever the things were in Harry Potter, like the sorting hat. Then we're wearing a discriminative hat. This lecture is entirely on the generative side of things, okay? And I say that just to keep it clear in your minds, not because I think one is better than the other, or that you should always do one or the other. That would be terrible advice. Just so that you can situate what I'm going to tell you. Everything we're talking about today is generative modeling. All right, so let's start off by thinking about how we can design probability distributions over this infinite set sigma star. There's a very simple trick you could do to make your life a lot easier, which would be to give probability to 0 to any sequence that's too long. So just pick a max length b, upper bound, and then make the distribution uniform over everything that's shorter than b, because that's a finite set. It's exponentially large, but still finite. And everything that's too long, that's longer than b, gets 0. And if you have, n examples, you can just put 1 over n probability on each sequence you've observed and 0 to the rest. And this would be a very simple thing to do, but we don't do that. And you can probably guess why. We want to build probability distributions that generalize. We want to be able to assign probability that's non-zero to everything that we could ever observe. So what that means is that traditionally, it means that we're going to go for some kind of parametric probabilistic model family. And then we're going to design algorithms that let us construct the model from data. And this is sort of, universal in probabilistic modeling. You choose your family, you decide what assumptions you're willing to make, and then you come up with algorithms that will fit the parameters of that model family to the data that you have. So here is the first kind of model you might come up with. It's a history, I call it the history-based model. And the key thing it does is it makes use of the chain rule, the probability chain rule, not the calculus chain rule. So you're running to define a joint distribution over the sequence of words 1 through n. And let's put a start symbol at the beginning and a stop symbol at the end to make life a little bit simpler notationally later on in the lecture. And what we're going to do is decompose this joint probability into a product where we generate each word in turn given the ones that came before, the ones to its left. So we're going left to right. We could have decomposed this lots of different ways. We could have picked any order at all, and the chain rule would have allowed us to do that. But the natural thing to do, probably because we speak left to right, or we speak from the beginning of the sequence to the end. I guess if you speak Arabic, you speak right to left. But today we'll stick to English, so we'll go left to right. The things that are to the left kind of come before, and so we can kind of think of proceeding left to right. People sometimes use the word causal or the word autoregressive to refer to a model that decomposes things this way. I tend to stay away from that language and just say left to right. Okay, and notice in my little formula here, I started using gamma to denote one of these single word given its history probabilities. And so I want you to think for now of that gamma of just being a parameter in the model. I'm going to estimate the probability of the word apple coming after the sequence start she ate n, for example. Okay. Okay. So one way to sort of visualize and make physical this idea is to use the metaphor of dice. By the way, small English thing. If you go to Las Vegas or gamble and you like to play games with these little cubes with numbers of dots printed on the sides, a single one of them is called a die. Plural of them is dice. So you roll the dice or you roll a single die. We're only going to roll one die at a time. So if that sounds strange to you, if you learn nothing else in this lecture, you learned an English word. Okay, so we have one die for every possible history in the universe that we could ever have. And we write down the start symbol. We pick up the die that corresponds to history equals start. We roll it. We get a word like I. We pick up the die that says start I. We roll it. And on every side of each of these dice, we have all the words in the vocabulary printed. So these little dice with 6 sides are really not big enough. We really need a die with, like, hundreds of thousands of sides, one for every word, but I couldn't find a picture of that. So, okay, so then we pick up the die for start I want, we roll it, we get A. We pick up the die for start I want A, we get flight, and so on. And notice that as I'm getting a longer and longer history, I have these more and more specific dice, one at each time step, that I have to pick up that are associated with really long histories. And I keep going, by the way, until one of the dice that I roll comes back with stop, and then I stop. This sort of special red stop to mean, like, really command stop, not stop the word in English. Okay, so that's basically the history-based model. This is sort of a natural place to start. This is a very rich model. It can actually represent any distribution that anybody could ever dream up over all the sequences in the universe in sigma star. But there's a downside to a model like this, and you may have realized by now, I need a lot of dice. I actually need infinitely many dice because I need one die for every single possible history I could ever encounter. So that's a lot. That's basically an infinite number of parameters. And also, this model has a serious problem. It won't actually, probably it won't generalize, because if I do the standard thing and estimate the probabilities based on frequencies in the training data, what's going to happen is that any sentence I didn't see in the training data is going to get 0 probability. And it's not too hard to show this. Basically, if I have a die for a history I've never seen before, I have no information about how to assign probabilities to the different sides. So this model is, when I teach it to my undergraduates, I call it the creepy model, because if you actually build it, if you try to implement it, all it will do is memorize the training data that you used to estimate the weights on the sides of the dice. So it really is just like a memorizing machine, and it's useful to sort of recognize the existence of this kind of model in the conceptual space of models, because sometimes people wonder whether the current models, the fancy neural networks that Hannah talked about in her research talk last night, and that everybody seems to be using in NLP, sometimes people wonder if they're kind of like this. Are they creepy models that just sort of memorize what they've seen? And it seems they're not. It seems they're better than that. But the number of parameters they have is very large, and sometimes they seem to have a creepy tendency to kind of repeat things that they saw in training. So this is sort of an extreme point, and it's useful to kind of pin it down. Here's kind of another extreme. This is called a bag of words model. It's really simple, and it basically makes a very strong independence assumption. It says every word in your sequence is completely independent of all the others. And in fact, it doesn't even matter which position you're looking at or what came before. You're just going to roll the same die every single time step, okay? And it's going to tell you the probability of each of the words. So you roll it, you get I. You roll it, you get 1. You roll it, you get A. You keep rolling the same die, and magically somehow an English sentence appeared, and then we get a stop symbol. And so really what's printed on the sides of the die are all the words in English plus this stop symbol. So this is kind of another extreme, and I like to point to it again because it's useful. Well, one reason is that people actually do use this model sometimes for very specific use cases, but it makes extremely strong assumptions. And what that means is that there are limits to how well it can fit the data, right? This model can't learn English. All it can really learn is English word frequencies, or I should say, whatever language. If you train it on Portuguese, it would learn Portuguese word frequencies. It doesn't do it's not going to memorize your training data. You can be assured of that. It's just going to remember how often it sees different words or what rates it tends to see different words. And the reason people love this model is that it only has one parameter per word in the vocabulary. All you're doing is estimating the relative frequency of each word type in the vocabulary. So that, if you want a small, lightweight model, then this is kind of appealing. And it also, it can generalize in a way that the creepy model couldn't. If you see a new sentence, as long as every word in that new sentence that you didn't see in training data, as long as every word was observed somewhere in the training data, you can give that sentence a positive probability. Okay, this idea that we want to be able to give everything we observe some positive probability has really been crucial to understanding the development of language models. Okay, so we've seen two extremes: the creepy model that has sort of infinite, arbitrarily long history for every word, and the bag of words model, which has no history for any word. The happy medium is called the Markov model. And the first thing we learn among the Markov models is the first order Markov model, where each word depends on one word that came before. So first order means I depend on one symbol of history. So here we have a conditional probability of the ith word given the I minus first word, just one. Okay. So this is, you should be able to imagine we only have one die per history word. So if we have V words in the vocabulary, we have V different dice, each with V plus one sides, one side per word, plus the stop symbol. We pick up the start die, we roll it, we get I. We pick up the I die, we roll it, we get want. We pick up the want die, we get A, and so on, up until we roll a stop symbol after the period. The probability of stop after a period is usually pretty high. This is kind of a nice, point in the middle. It makes a fairly strong independence assumption that each word only depends on the one that came before. That's probably wrong, right? That's not usually the way language works. Usually I'm trying to express a bigger thought, not simply picking another word given the one that came before. But, it's a little bit weaker than the bag of words model. Who can tell me how many parameters it has? Let V be the size of the vocabulary. Shout it out. V squared, order V squared. Maybe V times V plus one because I have to have that stop symbol, but maybe only V squared because once I lock in V of the probabilities, the last one is fixed because they have to sum to one. Sentences not seen in training, it's a little bit complicated. So if there's a new sentence I haven't seen in the training data, if every one of the bigrams, by the way, these two word pairs, the history word plus the word I'm predicting, we call them bigrams. If every one of the bigrams had been seen or for some reason got a non-zero probability and we multiply them all together, we should be fine. The only way that we would have a zero probability would be if we assign zero probability to any bigram. And there are ways to avoid doing that. Okay, so you can easily generalize this to mth order, where you have m words of history. And so, historically, these were known as bigram model, trigram model, fourgram, and so on. At various points in history, these were the way you did language modeling. Okay, prior to the rise of neural language models, I think the first neural language model was almost 20 years ago. But for 20 plus years before that, maybe longer, the way whenever we needed a language model, we assumed it was going to be some kind of Markov model. And what order you chose depended a lot on your problem, but really mostly how much data you had. So the way I learned language modeling, we would talk about if you had relatively little data and didn't need your model to know very much about language structure, you'd be far at the left, and that would be easy and fast. As you move to the right, you needed more and more data to estimate the parameters. The number of parameters grows exponentially in M, the order of the Markov model. Nobody ever actually used those entire history language models. They are just here for pedagogical value to kind of lock you in on the extreme case, but we would never go that far. I have distinct memories of learning trigram models were really hard to beat when I was a student. That should date me to a particular age. By the time these things were really cooking, when neural models came onto the scene, it wasn't uncommon to see people using 5-gram or maybe even 6-gram models in machine translation. I don't know. I do this, and I realize it's kind of funny to do this. I mean, well, we used to do this to show that even though these models are generative and they can be used to generate text, we generally did not do that And the idea that today we sample from language models or do beam search on the probabilities from language models to find high probability sequences to decode would have seemed crazy a few years ago. And this is why. If you take a unigram model and you sample text from it, you get stuff like this. This is not English. This isn't remotely English. If you sample from a bigram model, you get stuff like this, not English. Maybe if you were half asleep, you would think somebody was speaking English, or you had heard people speak English in the movies but didn't understand it. It might sound like English, but this is not English. If you go to a trigram model, it starts to get a little bit more fluent. As I can pin them all, none of them want to bet that any of the, it's sort of like starting to get there, but there's obviously no meaning here, right? And usually the result is not fluent. You can't make any sense out of it. When you go to 5 grams, he realizes fully how shallow and insincere conservative behavior has been. He realizes that there's little way to change the situation. Okay, this is starting. Like you could imagine somebody saying that. It's starting to get there. This is a 100-gram model, and all this is doing is essentially recovering. It's getting very close to that creepy memorize the data model. It's basically recovering instances from your training set. So this is like totally readable. Again, we never used n-gram models this way. We never used, sometimes they're called n-gram models. In this lecture, I've been calling them Markup models. We did not use them to generate text. We would combine them with other things. So this new world where we directly decode from a language model would have looked kind of absurd given the way language models worked just 10, 15 years ago. Okay, so that was the first piece, Markup models. This is where in a recent year, when I was making videos, I switched to the second video. So, come back up for air. We've introduced n-gram models. In this lecture, I like to call them m+1 gram models to remind you that m is the Markov order, m is the number of history words you're conditioning on, the +1 is the predicted word. What do we think? Well, these are really easy to understand as kind of a formalism or a technical model of natural language. They're fully generative. We don't really use them to directly generate, but we did use them to generate text in combination with other things. There's a set of algorithms that I want to walk through with you just to make sure you understand how we would put these to work. But I want to point out some of the negatives, right? So, no linguist, no one is anyone here a linguist? Training linguistics? Okay, you're probably like thinking this is the worst model of language ever. This is so depressing. This is clearly not, not gonna make any linguist happy. It doesn't tie the forms to any kind of semantics. There's no model of the syntactic structure of sentences or the regularities. It's all down to just words. Really, really kind of a disappointing linguistic formalism from a linguistics point of view, if the goal is to explain human language. And there's this big problem from a statistical point of view that as you get these richer and richer models that can generate more fluent text or be used to score more fluent text, you need you have more and more parameters, and it becomes really difficult to deal with the fact that most of the m grams or m+1 grams you want to estimate a probability for, you've never seen. So typically when we learned about language modeling, when we taught language modeling, your PhD advisor's advisor, when they learned about language modeling, several lectures would have been spent on how to smooth the probabilities to make sure that every m+1 gram gets something more than 0. And it was like a black art. There were all these tricks, all these formulas, you had to memorize them. We don't do it anymore. We don't talk about it because neural nets have made that problem go away, maybe. There's also no really elegant way to deal with unknown words. That's actually still, I think, kind of an issue to some extent. Now we have these like word pieces, and maybe that helps. But anyway, there were a lot of things that were unsatisfying about them, and it was very frustrating to people who were fascinated by language and found language itself to be an interesting driver of why we did NLP. That the n-gram model was so good at, it was like the best thing going. And every attempt to come up with something fancier just generally didn't have a lot of benefit. Anyway, let's because these are our stepping stone today towards something more interesting. Let's talk a little bit about how you can work with them. First, if we want to calculate the probability of a given sequence, somebody hands you a sentence, let it be n words long. We're going to have an M-length history. Here's how you're going to calculate the probability. And apologies if this is totally obvious. It's always good to have a couple points in a lecture when everyone can sing along and it feels like they already know what's happening. Just, otherwise you'd be exhausted. Take every consecutive m+1 words, call that an m+1 gram. Go look up the probability of the I plus m of them given the others in your probability table. Look up the stop probability given the last m words. And then you multiply these together. There's one, key technical thing I like to point out here. We almost never would multiply these together for real because these are usually very small numbers, right? We're dividing the probability mass over the entire vocabulary, tens or hundreds of thousands of word types. So these are little numbers, and if you multiply together a lot of little numbers on a floating point computer, you will likely get underflow. So what we would normally do is we would keep the logarithms of these probabilities and add them up. And then if you need a probability at the end, you would exponentiate the final number. Often we just work in log space. So these become high magnitude negative numbers that are added up. If I give you a set of sequences and I want you to choose the one that is most fluent under our language model, most probable, you can reuse that little algorithm I just gave you for each sequence in the set, calculate its probability, choose the one that has the highest probability. And so that is this is a very straightforward tool. You can imagine in a slightly different world, pre-direct end-to-end models, people had all kinds of ways of producing candidates that might be good outputs for an NLP system, for maybe a speech recognizer or a machine translation system. And then they would maybe use the language model to decide among this set, which one seems to be the most fluent, which one seems like the best English or the best Portuguese, if we're decoding into Portuguese. After something else, some other module generated the candidates, the language model could be used to try to pick one that seemed fluent. And that was not an uncommon thing. Finally, this is, again, something we didn't usually do with a language model directly before the most recent generation of language models, because they just didn't generate really fluent text. But if you wanted to, you could you could write down a start symbol and then repeat until you get stop. This is basically rolling the dice that I showed you on previous slides. You select the distribution that corresponds with the most recent M words, pick up the die, sample a word from that distribution. If you like Python, you might use this random.multinomial function, write down the word and repeat until you get a stop symbol. Very straightforward, very easy to generate. I don't really know Python, and it was easy for me to generate from those n-gram language models just by repeatedly calling a function like this. We have to say a little bit about training. Usually, again, people find this kind of intuitive and obvious. For each of the different kinds of Markov models we talked about, you're basically doing the same thing. You count up the number of times you've seen the whole n-gram, the whole m+1 words, and divide it by the number of times you've seen the history to get the estimate of the conditional probability. This is called relative frequency estimation. You can prove that it is the maximum likelihood estimate for the probabilities. And this holds no matter how long the history is. You're always counting the frequency of the history plus the word and dividing it by the frequency of the history. This is not actually what people would use, though. They would always do something to the frequencies before turning them into probabilities to make sure that everything got some non-zero amount of probability. And this is an old topic. I'm just going to skip over it completely because fortunately we have better ways to make sure our models don't give zero probabilities out. Okay, so brief summary of like 10 years of language modeling history. These things existed, smoothing existed. In the early 2000s, people started, the web was really on the rise, and companies like Google were building bigger and bigger and bigger language models, and basically finding that the more data you added to a language model when you trained it, the more effective it became at whatever you used it for, including things like speech recognition, machine translation. And so, more and more work went into coming up with efficient ways to work with these models. A lot of training and estimation on MapReduce architectures. And people came up with ways to compress these things so they would fit in memory. These are similar issues to what I think we face now with neural models, but of course the hardware was somewhat different, and the specific tricks you used were quite different because you were storing tables of probabilities and you had to do these lookups instead of really dense calculations like you have with neural nets. But a lot of the same patterns, we're showing even 15 years ago. We knew that more and more data made language models much, much better. Okay, really briefly, just going to point to the fact that around 2003, people started using neural networks to generate that vector gamma of probabilities over words given histories. So the first ones were little feed-forward networks that looked at word vectors associated with each of the history words and plugged them through some calculations to get the final distribution over the next word. Then people started using recurrent neural nets, which looked at essentially there was a dependency on the entire history of words. So this was really kind of an exciting breakthrough. No longer were we making Markovian independence assumptions. Every word in the history somehow influenced the probability distribution of the next word. That was kind of cool, but it came with some sort of technical challenges that I won't get into, but you either heard about yesterday or we'll probably hear about later in the week. Finally, most recently, we have this neural net called the transformer, which was basically designed to maximize the potential of GPU hardware. And rather than thinking of position in terms of when the calculation happens, position becomes kind of something that's encoded in the input vectors. And so in the end, it looks quite different mathematically from the kinds of models we're talking about today, but it's still doing the same job. So transformer-based language models like GPT-2, GPT-3 are still predicting the probability of the next word given the words that came before. They're still using maximum likelihood estimation to estimate the parameters of the model, but the parameters look completely different from my Ingram tables. Okay. Typically, when we were building these kinds of simpler, older language models, we tended to think about, well, I mean, even still, when we're modeling sequences, there's always some notion of like something is coming in and we're turning it into a sequence we're generating, or the sequence comes in and we do some analysis and we predict something else, one or the other, or maybe both. In the case of translation, we get text in and we have text going out. Sequence models actually pop up in both roles, in both of these scenarios, and they play different roles. The classic way of using them, I like to just kind of mention this because it's completely out of fashion now, but again, it provides a nice contrast. Who's heard of the noisy channel model? Is this familiar? Okay. This goes way back to even before HMMs, the 1950s. It was proposed as a model for how translation happens. When the Americans were trying to, win the Cold War, one of the things they fantasized about was being able to decode messages being sent by the Soviets. And so, they imagined that these messages from the Soviets were floating around, and we couldn't understand them because they were speaking this strange language, right? And so this one information theorist named Warren Weaver classically came up with this idea that really what was going on was the Russians were thinking in English, because of course. And the idea was that what we really needed to do was be able to decode the English they were thinking, which had been garbled up through their weird Russian speaking apparatuses. And we needed to degarble it and get back the original English that was in their heads. So the generative story they were telling, Warren Weaver was telling, was that there was a source model, P of Y, which generated English, the true Y. It went through this like blender-like thing, the channel model, that garbled it up. And what was produced was X, which is the Russian sequence. And so if we can model the two parts, the source model, which is a model of good English, a language model, and we can model the garbling or the translation in the reverse direction from what we really want, probability of Russian given English, so kind of a backward translation model, then we could decode using the rule at the bottom and try to pick an English sequence that is sort of both likely under the source model, right, good fluent English, but also faithful to the meaning that's expressed by the Russian, P of X given Y. And this was how statistical machine translation worked. Same idea was actually employed before that for speech recognition, where Y is the English sequence and X is the acoustic signal. It's been used for a whole bunch of other different things, optical character recognition, spelling, punctuation correction. Lots of problems were cast in this light. And sometimes the language model would also be would be used as the channel model. So you can cast problems like text categorization, language ID, some kinds of information retrieval, some summarization problems where you use a language model as the channel. Today, we do something different. Today, again, for contrast, we have an input. That would be the X here would be the Russian. You're not modeling at all. You're just plugging it in and you're trying to generate the desired output by modeling P of Y given X. This is usually, most people find this simpler and easier and more intuitive. There's no Bayes rule. You have a model, it goes in one direction. When you're decoding, you're basically going in the same direction as your model. This is the dominant approach right now, these kind of direct models. Who knows? Maybe we'll see the noisy channel come back, but it's useful to kind of have this, I don't know, alternative way of looking at the problem, I think, because estimating a P of Y that's just the English by itself is actually like, that's actually, we still know this today. This is the easiest thing. There's quite a lot of data that's just raw text. When you do the direct model, it's not actually totally clear how to make use of all that data. Everything that you're going to use to estimate this kind of a model, at least in the first design of this kind of model, has to be input and output paired together to get that conditional distribution. So I think a big long-running question in the history of NLP is, how do we make use of unlabeled text to make models better? And one of the earlier answers was you build a language model and then you use it as a component in this bigger noisy channel system. Today, the answer is different. You build a language model and that's considered pre-training for other tasks. Okay, anyway, n-grams are really fast to work with, really intuitive. They can fit the data really well. Every parameter can be understood and tied back to something very intuitive. They did not go out of date until the really expensive neural language models could be scaled up to very, very large amounts of data. It's kind of surprising how long n-gram models stuck around, and you still see them from time to time in certain applications. But generally, before the neural nets, people would sometimes get a little bit of gain by incorporating a little bit of task-specific knowledge to their language model, or a little bit of domain knowledge, a little bit of linguistics, and then usually once more data was available, those gains would be washed away. It was kind of a sad story of like more and more data tends to help better than fancier theories if you can get more data. Of course, we all know you can't always get more data of the kind you need. Okay, so the sort of add-on to Markov models that I think is a nice stepping stone to the big topic for today was something called class-based sequence models, introduced in 1990. The idea here was essentially to try to reduce the number of parameters even further. And so what the Brown group did was they incorporated a notion of each word being generated not based on the previous word, but rather based on a cluster identifier for the current word. So what you see here is CL of W it's a deterministic function that takes any word in the vocabulary and maps it to a coarse-grained cluster. And so the idea in your generative story is that you choose the cluster of the word, given the cluster of the previous word. And then after you know the cluster, you choose the word from a much smaller set. And so if every word only is assigned to one class or cluster, and you know it in advance, usually through some kind of clustering algorithm, I won't go into that. Brown clustering was kind of the most famous and successful of these. Then this model is kind of an interesting twist. Here's how it looks with the dice. I start with the start symbol, and then I choose the next class. So I roll the start die, and I get, say, C53, which doesn't mean anything on its own, right? That's just the identifier for the cluster. Then I pick up the die for class C53. Notice this is a different kind of die. It's red, for one thing, and it has words printed on it instead of classes. So I roll that die and I get the word I. And importantly, with this model, every word in the vocabulary appears only on one of the red dice. It's only associated with one cluster. So once I know the cluster, I've really narrowed down to a much smaller set of words. Then I generate the next cluster, say 23, pick up its die, generate its word, I get want, and so on. So this model is kind of interesting because it's not exactly like any of the models we saw before. It seems to have some kind of first order Markovian structure among the clusters or the classes, but the words have this sort of more interesting interdependency where they're conditionally independent of each other through their classes, and all the sequential modeling is done through the classes. How many parameters does it have? Well, it strongly depends on the number of classes. The dominant term in this model is going to be how many classes do you have, square that, and that's how many parameters you have for the gamma part. You also have a probability for each word given its class, but there's only v of those because each word appears only once on one die. How well does it generalize? That's an empirical question. But people got some nice results with this, and sometimes the clusters, depending on how you estimated them, would come out to be fairly intuitive. I remember from the Brown paper, one of the interesting things that happened when they built clusters of words based on contexts they occurred in was that all the days of the week landed in one cluster, and a whole bunch of verbs with, you know, similar meanings about like kicking or throwing or like sports type words all landed in one cluster. Okay, that's all I want to say about Markup models. Let me take a sip of water and somebody can ask a question. Come on, I did all that talking. You're ready for hidden Markup models. All right, we're already on video number 3. Are we going too fast? No, I don't think so. I think we are. You'll tell me to slow down if I'm going too fast. You won't. We're back to, it's like 2011 when the room was just silent. People forgot during the pandemic how to interrupt a lecture. Okay, so that class-based model is, it basically got us almost to the HMM. Okay, if you understood the class-based model, the HMM is going to be almost, in fact, the formula looks basically the same. But let's be a little more precise about it. So the HMM is a model, it's a probabilistic model really over 2 sequences. The sequence of symbols, yes, the words, but also a sequence of information associated with each symbol called its state. Okay, the word state, unfortunately, gets used in a lot of different ways. If you're familiar with recurrent neural nets, you probably have heard people talk about the state vector. Forget about that for now. Okay, states here are they're like United States. They're discrete, distinct entities. You can't be in 2 of them at the same time. They're not vectors at all. They're like different colors on the map. Okay. We have a finite discrete set of them, we'll call it lambda. And the idea is that each word that you see in the sequence was generated in a particular state at the time it was it was generated. And so what we're building is a joint model over both the sequence of symbols and the sequence of states that we were in when they were generated. And in the traditional setting of the HMM, those states are considered hidden, meaning when you see data, you don't know what state any particular word was generated from. So sometimes they're called latent variables, sometimes they're called hidden variables. But the key is that we don't know them at inference time. So here's the model. We start in a start state, we roll the die, that corresponds to the start state. We get C53, which is a state. And then we generate a word from its die. The only change from the Brown class-based model is that now any word can appear on any of the dice. So we do not know here what state we were in when we generated the word unless we observe the process of the generation. Okay, and then we pick the next state based on the C53 die. We roll it, we get C23. We roll the C23 die, we get want, and we continue. And we keep going until we get to the end. The last piece I should have put on the slide is that when we are done, this story disappears and all we have left are the words. We don't know the states. So when we observe data in the wild, we believe there was this story, right? It's the generative myth that each word was generated from some state, but we don't see the states. We can actually tell the story 2 different ways, and depending on which textbook you read or which lecture you watch, you'll sometimes see it, like I just showed it, as transition from state to state, followed by emission from a given state, followed by a transition, followed by an emission, black, red, black, red, black, red. Sometimes you'll see generate the whole sequence of transitions, writing down all the states you pass through, a Markov model on the classes, and then stochastically replace each class with a word. So black, 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 till you get to the end, then go back and replace classes with words using the red dice. They're equivalent, the probabilities will be the same, it doesn't really make a difference. If you prefer one or the other, that's okay. We can condition on longer histories of, did I turn this off? No, it's good. We can condition on longer histories of past states. So this is an nth order hidden Markov model. It was not uncommon to use second or even third order Markov model HMMs in earlier times. We'll stick with the first order version today for simplicity. But what I want you to see is that the number of parameters, it still grows exponentially, but only in the number of states, not the vocabulary size. So it was much more manageable to have a second or third order HMM than a second or third or fourth or higher order Markov model without the hidden states. So this is a way of kind of getting more out of your parameters, right? And of course, what you're doing, to use a term that often gets used with neural nets, as you increase the order of your HMM, you're giving a longer memory. I think you're doing this at the expense of some interpretability. There's something really delightfully pleasant about the first order HMM, where there's something is remembered by knowing what state you were in at a given point in time, but only kind of a fixed finite amount. The longer the state history that you're conditioning on, the more you're sort of kind of dragging historical baggage with you as you go from state to state. So I'm going to stick with first order HMMs today, but everything I tell you generalizes to the higher order case. All right. You can see the dates on these papers. There was a time when HMMs became like the tool of choice for modeling all kinds of things in NLP. Of the things on this slide, probably the one that you've heard of today is named entity recognition. That still kind of exists as a practical information extraction task, and many things look like it. There were these older problems around kind of shallow syntactic modeling of text, assigning words to syntactic categories like noun or verb, part of speech tagging. That'll be a running example in this lecture. Other things where you tried to chunk groups of words together in various ways or align them in parallel text. So you have English, you have German, and you're trying to line up which words correspond. This was a kind of a pre-processing step for many machine translation systems. They really caught on in computational biology, and for many years they were like an essential component in speech recognition. In that case, with continuous observations instead of discrete words. So HMMs were, before neural nets, they were probably the one model that almost everybody doing empirical artificial intelligence work could all kind of share in common. Everybody kind of knew about HMMs. Okay, so this is the part of speech tagging task. You see a sentence at the top in English, and then underneath you see these blue tags or labels associated with each of the words. They look a little bit cryptic. I think today I've kind of decoded some of them. Why they're abbreviated this way is not really important. If it starts with a V, it's a verb. If it starts with N, it's a noun of some kind. Plural nouns and proper nouns get their own tags and so on. This is one scheme for part of speech tags that was developed in one project. There were many others, but the key idea is that each of these words has kind of a grammatical function, and we can tag them. And many of the words are actually ambiguous. So in this example, the word bills could be a plural noun, but bills can also be a verb, like the medical company bills Francis every month, right? Or the insurance company bills Francis every month. I think also broke can be a verb or an adjective, right? And it's not uncommon for words to be kind of ambiguous in this particular syntactic way. And so part of speech tagging would help you resolve all these ambiguities by labeling each word. Named entity recognition, again, still kind of exists. I think people still publish numbers on this. You have a sentence here, and in different colors, I've labeled things that are special entities that get names In English, we tend to capitalize the names. I think in Portuguese too. Not always. There's always some exceptions, but a strong cue that a word is part of a named entity is that it is capitalized, even though it's not at the beginning of the sentence. Sometimes it's a person. Sometimes it's a place, like Kennedy Space Center. I added a space shuttle tag. The way we would solve this problem as a state kind of word labeling problem is to use a B to indicate that this is the beginning of a named entity mention, and I if it's sort of not, it's inside the mention, but not the first word. This is challenging because in human societies, we tend to name things after other things. Like Kennedy was a person, and then they named the Space Center after Kennedy. So in order to make sense of this sentence, you have to know that Kennedy Space Center is the place, not the guy, right? We reuse names a lot. In fact, the town I grew up in is named after Lisbon. So whenever I tell my mom I'm going back to Lisbon, she thinks I'm coming to visit, but I'm actually coming here. Okay, word alignment. This is a problem we don't see solved very much anymore, but it's still kind of cute. And you can kind of imagine why this would have been important if you were building machine translation models that didn't work end to end, and you wanted to estimate the probabilities of different words in English being used to translate different words in German. You might want to have this kind of data where you've linked up the words to their kind of translational equivalences on the other side. So this is two sentences that mean roughly the same thing in English and German. There's some extra stuff on the English side, both because of English grammar and because translations are usually not 100% exactly faithful. But the idea was you could treat the German words as states and imagine walking among the states and generating English words as you go from their German equivalents. And so the HMM could be used and was used 25 years ago or so to estimate the probabilities of the English words given the German ones. This is German. But okay, so from here on, I'm not going to worry so much about what the states mean. You can probably think of other applications. You could probably think of, if you work in conversational text or dialogue processing, HMM states had a whole other set of use cases and applications. We're just going to be very abstract and think about these states. I'll probably call them states sometimes and classes sometimes. They're all the same when we use a first order HMM. All right, so you've seen the model. Hopefully it's fairly comfortable. The remainder of this lecture is going to be about various algorithms that you might use to do different kinds of calculations with the HMM. So the first one we'll talk about, and that will, I think, get us roughly to the coffee break, tries to find the most probable state sequence given the words. So you see the word sequence, you have your HMM already, and you're trying to figure out what states you most likely pass through to generate those words. Or I shouldn't say you, the HMM. And then we'll talk about some other things you can do with HMMs. For example, you can use them as language models. You can use them because they give you the probability of a sequence. You can sum out the probabilities of the different state sequences you might have passed through to get the total probability of the word sequence. So you could use an HMM just to score word sequences without ever worrying about the states or caring which ones you pass through. You're just treating them as a latent variable and you're summing up over all the possible values they could have taken. We can also do local things like calculate the probability distribution over the state for a particular word. This was used in a variety of settings in the past and still comes in handy maybe if you're using an HMM and want to do local reasoning about some pieces of information in the middle of a sequence. And then we're going to learn an abstraction called the minimum risk sequence, which generalizes several of these things. And then finally, we'll turn to learning and talk about how you learn the parameters of the HMM. So the gammas, again, are the transition probabilities, the probability of going from any one state to any other state in a transition, and the etas are the emission probabilities, the probability of generating any word given any particular state. So the first problem, the most likely state sequence. The HMM is trained. We have all the parameters stored in a handy data structure. We receive a symbol sequence W, and what we want to do is find the state sequence S that is most probable given the words we've observed. If you're a statistics person, the technical term for this is maximum a posteriori inference. That probability that I've written on the inside the max is called the posterior probability over the states. If you are a computer scientist, then you are going to think about this as a discrete combinatorial optimization problem. There are a lot of state sequences, right? If we have an n-length sequence and we have L states, then there are L to the n possible state sequences we need to choose among. That's very large. How do we do this? This is an example of a sentence that is especially ambiguous. It's kind of contrived, but because almost all the words in this sequence could get different parts of speech, it gives a nice example of how even if you know something about each of the words and you know which possible parts of speech it could have, there are 4,000 options here for this short 7-word sentence. So our goal is going to be to figure out an efficient way to choose among them jointly so that every word's choice makes sense, not just for the word, but also in the context that it appears in and with the choices you've made about the other words. All right, so if I told you there are only 4,000 sequences, you might say, okay, well, we can just list them all, score them using the HMM and pick the one that's the highest. And that would be absolutely correct. You could do that. It would give you the right answer. It would be inefficient. It would not scale well to very long sequences. Suppose I told you I really want to do part of speech tagging on this whole book. Right? I want every word in the whole sequence, and I want to be, thoughtful about it. Ideally, I'd like every instance of the same name to be tagged the same way. This would probably not scale. There's an answer that a lot of people will give that is not the worst thing in the world, and in fact, it gets used sometimes. So we'll point to it. Just so you appreciate what you're getting and what you're giving up. You could work left to right and greedily pick the best state based on the previous state and the word that you're looking at. And the HMM even sort of suggests a way to do that. You look at the transition from the previous state, you look at the emission probability of that given word, and you just pick the max and then nail down that decision and move on. This is kind of a greedy left to right strategy. People often do that kind of thing. I've done it myself when I cared mostly about speed. The annoying thing, if you want to be really fastidious, is that it's not correct in the sense that it will not give you the highest probability sequence of states in general. And the reason is that it's not looking to the right. So what happens later on in the sequence can actually influence what you believe about the label or the state for a given word earlier on. That may seem counterintuitive because when we generate with the HMM, we're always working left to right, right? We transition from state to state to state and generate the words as we go. But if you think about it more from a sort of information flow point of view, you might see a word farther on that tells you something about what happened in the deeper past, in principle. And so while this strategy is very efficient and it's usually not terrible, it's strictly speaking not going to give you the highest probability state sequence given the entire word sequence. It's doing something else. But it's fast. So you have my permission to use it if you feel that's the best choice for you and your trade-offs. But that's not what I'm going to focus on today. Today, what I want to focus on is what if we really believe our model, right? There's maybe good reasons not to completely believe our model, but this is a model we computationally actually have the choice. We can believe it and say, I really want the highest probability sequence of states given my words. And I recognize that each word's label depends on the labels, not just to the left, but also to the right and the word itself. So in this little diagram, I'm showing you, I want to choose whether forecast is a noun or some kind of verb. And if I look to the left, each choice for the word present or present, depending, is going to point me toward a different choice. So if I believe present is an adjective, then probably forecast is a noun, because usually adjectives don't come right before verbs. And similarly, if the word is happened to be a verb, I would probably prefer a noun, whereas if is was actually eyes, which is a plural noun, a very uncommon one, then I would probably prefer a noun before it. I guess it doesn't matter. Either way, the word is probably prefers this to be a noun. But the word forecast by itself most commonly is a past tense verb. So its preference is something completely different. How do I mediate among these preferences given the left context, the right context, and the given word? The interesting point is that under the assumptions of the HMM, while there are these complex dependencies among the labels for adjacent words, the other labels, the ones that are farther away, don't actually matter. And it's that independence assumption that the distant past doesn't affect me except through the most recent label that lets me come up with a very efficient solution to this problem and jointly solve for all the labels. To understand how the Viterbi algorithm works, we start with the last label. Okay, so we look at the last word in the sequence, and let's just take for a moment, pretend that we knew the label for the n minus first word, the penultimate word, wn minus 1. If we knew its label, then we could come up with a score for any possible label in the last position by multiplying together three things. The probability of the stop symbol, which we know is there because we know we're at the end of the sequence, given that candidate, sigma. The probability, the emission probability of the word n, given that sigma. And the probability of that sigma, given that preceding state, n minus 1. Those are the only three things we would need, and we could score all possible labels sigma, and then choose the one with the highest label, and we'd be done. If we know that we're at the end of the sequence, and we know the label of the n minus first word. Which of course we don't, right? That is a fantasy. But the interesting thing is that if I knew the score of every preceding sequence, without knowing exactly which one was the correct label in the last position, I could reason about that last label. And in fact, I wouldn't even need to know that whole sequence. I would just need to know how it ended. I only need to know the most recent label to make my choice about the last one because of that Markovian independence assumption among the labels. So what I really only need is something simpler. I need to know the score of the one best sequence ending in each possible Sn minus 1. Okay, so imagine I'm making the decision about Sn. If I've done all the pre-calculations that tell me the score of the best sequence for each candidate in the step before, then I can think about Sn and I can make my decision. So everything, all the hard work in the Viterbi algorithm is really, you can think of it as a whole bunch of pre-calculation that lets me make a choice about the very last state. All right, so here's the recurrence. I'm going to use that same notation score, only with a subscript n minus 1 to refer to the scores of the best sequences of length n minus 1 ending in a given sigma prime. So assume we've done all of that. We've done the pre-calculation. Then my choice for the very last state is going to be to use this scoring function, now score sub n, the score of the best n length state sequence ending in sigma. I don't care what that sequence is. I only care that it ends in sigma, and its score is going to be given by exactly what I gave before. I have the probability of stopping after that candidate sigma, the probability that that sigma generated the nth word, and then I'm going to choose the best possible predecessor sigma prime that transitions into this sigma and has its own score for the n minus 1 length prefix. The main thing I want you to see here is that this is a recurrence. There's a score sub n, and it depends on score sub n minus 1. The same recurrence gets played out at every time step. The only difference is that the stopping probability is only used in the very last round. I don't need it earlier because there's no stopping yet. And it bottoms out. If I go all the way back to score sub 1, well, I know that the state before time step 1 was the start state. So I have a transition from start to sigma, whatever sigma is, and a probability, an emission probability of generating word 1 given sigma. And that gives me score at time step 1. Okay, so what's actually going to happen is I start at the bottom. I calculate this because it has a closed form, and then I use the scores from round 1 for round 2 and the scores from round 2 for round 3 and continue up until the end. Here's the algorithm for calculating the scores. I've literally just reversed the order. I start with the prefix of the sequence of length 1. Once I'm done with those, I reuse them to calculate the scores at time step 2. And I keep repeating this up until n-1. At the very last round, I have to do something extra to get in the stopping probabilities. And so my claim is that once I've done all of this, the score of the very best sequence of labels from the beginning to the end will be the max over this final vector of scores over all sigmas, over all possible final labels. I'm not going to walk through this proof. It is tedious, but I'm going to show you kind of a visual sketch. So look at the ceiling for a second to clear your visual memory. And now look back at the slide and don't be alarmed. Everybody's blood pressure just shot up. Don't read it. Don't look at it. What I want you to see is that I start off with a max of products, of maxes of products. And what I'm basically doing is I'm unfolding each of the scores on the right. Notice that up here it's n-1, here it ends in n-2, here it ends in n-3. I keep going and unfolding the scores using the same recurrence. And what you start to see is max times. What I'm doing is I'm moving from a max product, to one max all the way over on the left because of the property of distributivity. So I can, once I've unfolded this as a max product, I can move all the maxes over. And now I can think about it as a max over all of these exponentially many sequences of just a big product. And the big product is in fact the formula that I gave you for the HMM, probability of a sequence and its labels. Okay, this is not super important other than the fact that the reason the Viterbi algorithm does the right thing and gives you the right answer boils down to the property of distributivity and the really strong independence assumption, the Markov independence assumption among the labels. Each label only depends on its adjacent neighbors. Okay, so if I ran the Viterbi algorithm on this little example, I might get something like this table with all these tiny little numbers in it. I'd probably actually store their logarithms. That table wasn't really what I asked for. What I really wanted was the best label sequence. This doesn't tell me the best label sequence. It just tells me a bunch of numbers, a bunch of prefix scores. So really everything I just gave you was just the pre-calculation. We haven't actually labeled anything. We don't know any of the words labels. Well, we know pessimistic is an adjective because it can only be an adjective in this model, but that's just sort of, dumb luck. Okay, so to recover the best sequence, we have to do a tiny bit more work. All right, it's not a lot. We've actually done the vast majority of what we needed to do. We've done. We have to do a little bit more bookkeeping though. So if score sub I of sigma is the score of the best sequence labeling up through the ith word, ignoring what comes later, remember that it's choosing a max over all the possible sequences that could have come before for all the preceding words. If I happen to know what that next state was at the next time step, then I could use the scores to choose the label at the ith time step. So basically, I'm going to work backwards and label once I have the prefix scores calculated, I'm going to choose the label for the last word. Just like I said at the beginning, that's how we start. We label the last word, and then we use that label to choose the label at the I-1st position. And we keep going back to the left. Sorry, I should be going this way. And the solution to this is to keep back pointers. Every time we make a choice in the pre-calculation, we're going to keep a back pointer to the state that gave us that choice. So basically, along with each word, we're going to store a pointer to the preceding cell in the column before. This data structure, by the way, I call it a chart. And it's very common in dynamic programming algorithms like the Viterbi algorithm to have a table where you stored all of the pre-calculations and then an operation where you walk back through those steps once you finish the table to make your actual decisions. So here's the algorithm again, this time with the back pointers. Every time I choose a max here, I store the argmax. I store the sigma prime from the label set that gave me this best score here, so that when I'm done, when I get to the very end, I can recursively walk back through the table and make my choices. So here we call that the back trace. After I have all the scores and all the back pointers, I start by choosing the last state to maximize score sub n, and then I let the n minus first state be the back pointer associated with that particular label, and I keep walking back. And so I just follow this recurrence and pick the state at each time step given the one that came after it. Here's another example. Time flies like an arrow. I picked this one because the word arrow is actually not, it doesn't appear in the standard training set that was used for part of speech tagging. And so when you don't know, when you see a new word in this kind of world, you resort to like smoothed probabilities where every state can assign some tiny probability to an unknown word. And so there's really a lot of uncertainty about arrow, but I think this model will still make the right decision, label arrow a noun, given that it follows, and that's the most common thing, to have and precede a noun. Okay, so that was the Viterbi algorithm. Viterbi is, in my view, a really nice example of something practical and useful that instantiates this classic idea of dynamic programming, which is a beautiful idea with a terrible name. Right, the word dynamic programming, it confuses lots of people. Just think of it as a non-compositional compound. It is not dynamic. It is not programming. It's just an algorithm. It's like a type of algorithm, right? I once asked a famous NLP researcher if he could define dynamic programming because I was having trouble with the name, and he said, "Oh, it's one of those algorithms where you have a table, and you fill in the table with these numbers, and then when you're done filling in the numbers, you get the answer." So there's almost always some kind of table data structure. And it stores these partial quantities that you reuse. The key thing, I think, is that you reuse each of those quantities because the problem has what's called optimal substructure. The best solution to a problem relies on the best solutions to its subproblems, its similar looking subproblems. So the best solution to score sub n relies on the solutions to score sub n minus 1. And those subproblems overlap. They get reused many times. Every element in the ith column of that table gets used to calculate every element in the I plus first table. So every intermediate quantity that you build in doing the Viterbi algorithm is going to pay off because you're going to reuse it so many times. The Viterbi algorithm is my favorite. You've probably seen algorithms for string edit distance, like the Levenstein distance, or it's not usually taught this way, but Dijkstra's shortest path algorithm can be cast as dynamic programming. There are many others. And it used to be really pervasive in NLP that we had Viterbi, but then we had lots of variants of Viterbi, and people have come up with, things like semi-HMMs that make weaker independent assumptions, and they have their own algorithm that looks like Viterbi, but it's a little different. Once you understand Viterbi, you're kind of empowered to think about doing calculations over exponentially large spaces with models that make the right kinds of assumptions. People sometimes like visualizing what's going on with Viterbi, and I think the most beautiful way to think about it is best path. It's like a best path algorithm. So you know that before your sequence started, you were in a start state. That's the green one. And you know that at the very end, you were at a stop state. And at every time step in between, passing through one of these little blue states, one of these little blue nodes, vertices, implies that you've chosen a particular part of speech or a particular label or state for one of the words. And what you're doing when you run the Viterbi algorithm is you're choosing the best path from green to red, but notice that there's a very special structure to the way that the edges in the directed graph look. You can only go from one time step to the next, and you only pass through one vertex in a column when you cross a path. What we're doing when we run the Viterbi algorithm is we're essentially finding the best path through a graph that looks like with this special structure called a lattice. Let's take a minute to analyze this algorithm. You saw the table. It was a nice grid. It had one column for every word, n columns. It had one row for every possible state. There are lambda of those. So the memory requirement is n times lambda. Each cell in that table, it's a little bit deceiving. You might think that's also the runtime, but each cell in that table involves this maximization over something from every one of the previous cells in the previous column. So there's actually order lambda operations per cell. So your total runtime is the length of the sequence times the square of the number of states. So there is kind of an unpleasant cost if you want to do HMMs with very large numbers of states. So typically, you know, depending on what decade you're in and what kind of hardware you have, that would have a big effect on what sized HMM and how many states you'd be willing to consider. Oh, coffee. We have a couple minutes. We're supposed to do this at 12:30. I don't want to send you out there and have there not be coffee. So now is a great time for questions. I don't think we've had any yet. So now you have to hold up your end of the deal. Ask me questions, please. Please don't do it when I'm having my coffee. Do it now. There's a mic coming to you. Hi. No, it's not.
Could you talk about differences between Viterbi and beam search today?
Yes. The question is about differences between Viterbi and beam search. So basically the key difference, you can use beam search with this kind of model, right? So if you wanted to build an HMM with like millions of states, you can use beam search to try to find the best sequence. The key difference is that, you know, if you're super fastidious like me, beam search has no guarantee, right? Beam search does not find the best sequence under the model. There's a recent paper that is quite interesting that argues that beam search is optimal for some other criterion that has to do with like the entropy of over the states or something like that. It's a really interesting argument. I can't remember it now, but there is some criterion for which beam search is optimal, which is kind of interesting. But you can apply beam search here and get an approximate answer or an approximate k-best list. And that's a very reasonable thing to do if you have a very large state space. The advantage here is more theoretical. You get the model's favorite, right? You can also, it's worth noting, you can do interesting things to the Viterbi algorithm. There is a way to generalize it so that it gives you not just the one best sequence, but the k-best sequences with a guarantee. But it all hinges on, the only reason you get that optimality is the independence assumptions that come with the model. So this is, you know, really sharp contrast to today's models based on neural nets, where you give up the independence assumptions and that buys you something, but you give up optimality when you do inference. I don't think it matters that much, honestly. That particular thing, I don't think matters that much.
No, thanks. If you look back like more than one state, would it still be like then programming to solve it?
Yeah, great question. So, so if you move to say a second order HMM, where each state in the generative story, each state depends on the two previous states. So it's like I look at my two previous states, I pick up a die corresponding to those and roll it to choose the third. Second order HMM, you can solve this exactly with dynamic programming. It's a little more complicated. The memory requirements and the runtime requirement is higher. The runtime requirement, you have to store more, and the runtime goes up to being, I think, cubic in the number of states. So things go up in a nasty way as you increase that history, but that was still considered quite practical. It was not uncommon for HMM type solutions to things like named entity recognition to use a trigram. It was fine, yeah. When you start getting to like hundreds or thousands of states, it starts, you know, getting bad. And then you might just go to beam search, right? More questions? Okay, we've covered a lot. We've laid the groundwork for a bunch of algorithmic stuff that's going to come in the second half. All kinds of fun tricks you can play with these models. I will quickly review Viterbi when we come back, so let it sink in, enjoy your coffee, and we'll chat more in a half an hour. Yeah, okay. Welcome back. Let's dive in again. I'm always delighted to see people come back after the coffee break. You never know. Maybe you feel you learned enough and you're going to go get an early start on the afternoon lab. Or go to the beach. I don't know. Okay, so we've covered Markov models, we covered HMMs, we covered the key algorithm, the one that once you understand the Viterbi algorithm, it's much easier to unlock all the other secrets of hidden Markov models. I'll just sort of briefly recap. This is the whole thing. The core work of the algorithm, the hard part to understand and implement, the bug-prone part, is the calculation of these scores, which are, you start by calculating score 1, which is the score of one length prefixes of label sequences ending in each possible sigma, each label sigma. And that has a nice closed form. And then you iteratively use the previous round, the previous time step of score vector, score I minus 1 to calculate the scores at time step I. Each one of those involves a max over the previous label. And you also store the argmax as a back pointer so that you, at the end, can trace back to the beginning. And then finally, when you get to the end, there's this one extra term for score n to make sure you account for the stopping probability. The back pointers then can be used recursively to trace back. The interesting thing about the Viterbi algorithm, I was commenting on this to someone as we were walking out for coffee, is you don't actually make any decisions until you're done with the pre-calculation. You have to get the entire set of scores before you label even a single one of the labels. So if you want to make a connection, another connection to beam search or to other algorithms that do search, one of the things we often try to build into search algorithms is a kind of notion of looking ahead, estimating the value of different choices based on what's coming in the future. The Viterbi algorithm actually has look ahead all the way to the end. You don't make any decisions until you've made it all the way to the end of the sequence. There's often a feeling when you're calculating the scores like you're ready to make decisions, but you do not make any decisions until you're completely done scoring everything, and then you work backwards. Okay, so the Viterbi algorithm is it answers one question. It tells you the most probable state sequence given your HMM already trained and one sequence of words. I also sometimes like to think of HMMs as being able to do this other thing, which is behave like a language model and give me the probability of the word sequence. The main reason we might want to do this is again, language modeling. We have two or more sequences to compare. We believe the assumptions of our HMM are better assumptions than that of a Markov model. And so we're willing to do a little bit of extra computation to get better probabilities of the language model scores of two or more sequences. And the other reason we might want to do this is that we might want to train the HMM as a language model. Or we might want to train it to maximize the probability of the words that we see without knowing anything about the states. And this is actually one of the key ways to train the parameters of the HMM when we have only words observed, when we have sort of incomplete data. Okay, so I'm going to draw kind of an interesting parallel here. On the left, we have the problem solved by Viterbi. We wanted to find the state sequence that maximized the joint probability of that state sequence together with the words under our model. And we found that this was a combinatorial optimization problem and we could solve it in poly time. What we're interested in now is the marginal probability of the words given the parameters. So notice that this expression doesn't mention the other variable in the model, the states. If we want to be very explicit about this probability, it's a marginal, and we have to marginalize over all possible state sequences that could have generated the words. So here, what we're interested in, it looks very similar. Here we have max over S. Here we have sum over S. And it turns out that everything we exploited to get the Viterbi algorithm to give us this quantity in poly time, we can exploit here as well in the summing case. So we're going to use the same trick. And the key trick is to call these sort of partial sums up to a particular time step f sub n or f sub I at time step I. And so there's a similar recurrence where the sum over all possible state sequences ending in sigma depends on sums of similar form that only go up to time step n-1. So this is the basic recurrence of what's called the forward algorithm. And the only real difference between all of that math on the slide and all the math I showed you on the Harry Matthews slide before is that we have sums instead of max. Okay, and so everything we said about max, that distributivity property, it holds here too. So here's the forward algorithm. Without further ado, it looks almost exactly the same as Viterbi. You have to look closely to see the difference, and it's that here, everywhere we had a max before, we now have a sum. And I call the partial scores F for forward instead of score. But other than that, it's really the same. And we don't need back pointers actually, because we're not interested in any particular sequence of labels. We're only interested in the summation, right? The goal of this was to get a number. What is the probability of this sequence? So this is quite beautiful. The forward algorithm is it's a very elegant. In fact, sometimes it gets taught before the Viterbi algorithm because I don't know, maybe people were teaching the training algorithms earlier in their lecture than I am. Have people seen the forward algorithm before? Curious, a few people? Yeah. It turns out it's an instance of some things that come up in other settings as well, but we'll get to that a little later. But there it is. That's the basic idea. You can also come back to this lattice picture. Again, remember every path from the green to the red vertice, from the green vertex to the red vertex is it corresponds to a choice of labels for every word in this 5-word sequence. What we're doing here is we're calculating the sum of the scores of all the paths rather than the max of the scores of all the paths. But we're using the same decomposition. Before it was max product, max product, max product. Now we're doing sum product, sum product, sum product. So sometimes the forward algorithm is called a sum product algorithm for that reason. There are a lot of ways you can look at this problem. One of the lesser used ones is that if you think of the different f sub I scores as free variables and write out all the equations, you'll see it's actually a linear system with size of lambda times n free variables and one equation for each of them. So you could write this as one big matrix inversion problem. I don't know if anybody's ever done that. That's not a particularly attractive, efficient way to solve the problem, but the fact that it can be written that way is kind of intriguing, I think. Okay, so the forward algorithm is pre-computing these partial sums of label sequence scores from I equals 1 up to n. And each one involves lambda quantities, each over a sum of lambda combinations. So the asymptotic analysis is the same as the Viterbi algorithm. It's lambda squared times the length of the sequence. Intriguingly, I sort of assumed that I would start at the left and move to the right, and that probably shows some kind of cultural bias. You could do it the other way too. You can start at the right and move to the left. That's called the backward algorithm. It turns out that's equally useful. We'll come back to why later. But basically it has, do I show it? Yeah, here it is. Starting at the right, starting at n, there's a closed form for b sub n, and then we work backwards, n-1 back to 2, and use the recurrence. And it's all very, very similar. It's using the same trick of decomposing a massive sum into sum product, sum product, sum product. It's just organizing the calculations in a different way, going from right to left. And you should get the same answer, by the way. If you implement the forward algorithm and you want to double check you can go ahead and implement the backward algorithm and make sure you get the same answer within floating point error. Different intermediate quantities. So the forward scores and the backward scores, of course, except for at the very end when you calculate the final sum, they're going to be different, right? One of them is scores of prefixes of labels. The other is scores of suffixes of labels. Okay, here's a pop quiz. Could we have done this with Viterbi? Could we, we chose to implement Viterbi as doing these scores from left to right and then working backwards at the end. Could we have done pre-calculation from right to left and then labeled the sequence from left to right after we had all the pre-calculations? What do you think? Only if we have assume we always have a start and an end symbol. Those come for free. They're really easy. They're basically notational sugar. Yes? No? Who says yes? That was not enthusiastic. Who says no? Okay, I'm curious why. Does anyone want to give an answer? Explain why no. It couldn't be that easy. The world is not so symmetric and beautiful. In this world, it is. So the yeses have it. The correct answer is you could easily write a sort of backward Viterbi that organizes the calculations in the opposite direction, again using the distributivity property of max over times. So I don't know if I've ever seen anybody do it. Maybe it pops up somewhere. There's no particular reason I think you would, but you could do it. You could do it. Okay, so what's interesting to a lot of people about these two algorithms, Viterbi and forward, let's just take the left to right versions for now, is that they're doing kind of exactly the same thing, right? The structure, the control structure, the loop structure, everything is the same except for the choice of the operator, the max or the sum. And so that's kind of an intriguing point. So I'd like to kind of go on this little tangent and point out that there's a way to look at these things and say they're actually the same algorithm. They're exactly the same. It's just that you plug in a different, what's called a different semi-ring. So what is a semi-ring? A semi-ring is an idea from abstract algebra. I'll define it formally in a second, but it's basically a set of values and you choose some operations that obey certain properties over those values. So here's a semi-ring more formally. You have a set of values. One of them is designated a 0. Which means it's an additive identity. You can add it to anything and get that thing back. And you can multiply it by anything and get back 0. So in the real number semi-ring, 0 is 0, not surprisingly. And then you have something called a 1, which is a multiplicative identity. If you multiply it by anything, you get back that thing. And so the two operations you need to have in a semi-ring are an addition or a plus and a times. They're both associative. The plus is also commutative. And then critically, the thing we've been exploiting is that times distributes over plus. Okay, and I'm putting these in quotes because they don't necessarily need to be multiplication as you learned it in school or addition as you learned it in school. We can plug in different choices for the operators and for the 0 and the 1 and the set of values we're considering and get back different semi-rings. So here are the two semi-rings that we've used so far in this lecture. The reals. It's actually the non-negative reals. These, in this case, they're really probabilities. The 0 is 0, the 1 is 1, the plus is plus, the times is times. This is the familiar world you've known since you learned to do addition and multiplication. But there's this alternative semi-ring. We'll call it the Viterbi semi-ring. It has other names too. Over the same set of values, but here we never actually do addition. We do max instead. And it's just kind of a different algebraic object, the Viterbi semi-ring. When you instantiate the forward algorithm, but instead with the Viterbi semi-ring, you get the Viterbi algorithm. And there are many more. Intriguingly, we can use the same abstract algorithm with different semi-rings to get different things out of that same algorithm. So one thing you can do is you can say, forget about probabilities. Let's treat the HMM as a purely symbolic model. We don't care how probable things are. We just want to know what's possible. So any value that is 0 in the HMM, we leave as 0. Anything else, we map it to 1. And now the forward algorithm will give us this sort of Boolean thing where all we're really doing is anding and oring to decide what's possible. There's another version of this where we can change the semi-ring slightly and count how many valid labelings there are. This is quite easy if all the probabilities are non-zero, but if you have some things that are zero, or you have some hard constraints encoded in your HMM, like some labels can't follow some other labels, then this could be useful for understanding the amount of ambiguity that's encoded in your model. One thing people often do in practice is they replace probabilities with log probabilities, and then they replace the plus with something called log plus, which can be implemented very efficiently. And this is a way of avoiding the underflow problem we talked about earlier. There are k-best versions. I think I mentioned that in answer to one of the questions. There's a version where instead of maximizing, you try to minimize a cost, and that's the semi-ring that you usually see in classical dynamic programming algorithms like Levenstein, edit distance, Dijkstra's algorithm, and so on. And there are many more. So one of the interesting games people used to play with the Viterbi algorithm and friends was to come up with new semi-rings that would give you new interesting calculations. Okay, so now we have the forward algorithm and its sort of weird backwards analog, the backward algorithm, in addition to Viterbi. And now there are a whole bunch of interesting things that we can build on top of that, that I'd like to point to, again, to emphasize that with when you have a generative model and you make some independence assumptions, there are often a lot of alternative questions you can ask of your model and a lot of alternative things you can get it to do that maybe are useful. So far, we focused on reasoning about the entire sequence of states. We wanted to know the marginal probability of the whole sequence of words or the single best sequence of states over those words. All the local reasoning that we did was just about the total highest scoring sequence or the total probability of the words. One of the things that is useful to do when we start thinking about other quantities is to decompose that big sort of those big optimization problems or big summations into a smaller set of choices. So I like to use a graphical model representation. So this is a graphical model representation of what happens in what an HMM is doing. The key thing you have to get used to here, the circles are all random variables, and they're all relatively simple random variables, like a single word or a single state. And the arrows here are telling you what other random variables are the choice directly conditions on. So for a word, remember in the HMM, each word conditions directly on its state. We simply look at the state, pick up the die corresponding to that state, and roll it to get the word when we generate. States only depend on the previous state. So every node in this graphical model has a single parent, which is either the state that came before if it's a state, or the current state if it's a word. The general form in this kind of graphical model for the total probability of all the random variables taking the values that you see is a product over every random variable, its probability given its parents. And in this very simple model, every node has only a single parent. You can imagine a slightly more complex one where each of the states depends on two previous states, and then we'd have extra arrows hopping over each state. Okay, so that's kind of a high-level introduction to what a graphical model is telling you. It's mainly encoding the independence assumptions. Each word depends only on its state directly, and each state depends only on its predecessor directly. And where are the parameters? This is really complementary to the kinds of graphs that you see in papers about neural nets, which emphasize intermediate quantities that are calculated. Here, the parameters are hiding inside the edges, right? They are probability distributions over the child given its parents. So the gammas, the transition probabilities, are hiding in the horizontal arrows. The etas, the emission probabilities, are hiding in the vertical arrows. Later, we'll make them more explicit, but for now, we'll keep them kind of hiding. So I want to revisit the things that we covered earlier in the lecture in terms of this notation, because it'll be really helpful for the things that are to come. I like to use colors to designate the roles that the different random variables are playing. So for example, the sequence of words, when I was trying to find the most likely state sequence, I assumed that I was given a sequence of words. So I color the words gray to indicate that they are known, they are observed, they are seen. There's no need to reason about them. When the goal is to assign a value to a state, to a random variable, we're going to color it red. So in this case, we colored all the states red because we were interested in choosing labels for each of the words, choosing a state that went together with all the other states being chosen and the words as well as possible. So the goal of this graphic is depicting is to calculate the best value of the probability for any assignment to the red random variables respecting the gray ones. And with a little bookkeeping, we also recover the values that we assign to those random variables, the red ones. When we move to the problem of summing up over all the state sequences, we're doing something different. We're not actually interested in assigning values at all. Instead, what we want is to marginalize over all possible assignments, or sum up over the scores of all possible assignments to the things we colored blue. So when we used the forward algorithm, we were interested in summing up over all possible assignments to all the states. So we colored them all blue. So the general goal when we use these colors is going to be calculate the best value of the probability for any assignment to red random variables. In this case, there aren't any, respecting the gray evidence random variables and summing up over all possible assignments to the blue random variables. So here we have no red ones. In problem 1, we had no blue ones. So here's problem 3. It has red and blue. The goal is to choose the best value for example, state 3, without choosing any of the other random variables, instead marginalizing over them. So this is kind of like, I don't really care about choosing labels for all the words. Word 3 is just super interesting to me. Maybe I'm doing a linguistic study on ambiguity, and I want to take a very large corpus, and I don't really want the tags for all the words. I just want to reason as best I can about the likely tag for every instance of, I don't know, what's a word that's ambiguous. The classic example is bank, right? A bank can be a river bank, or it can be a place where you store money, or a place where you store blood, or I don't know, some other things. So I want to reason over the sense of the word bank, and I'm going to use an HMM to consider the senses of all the words, but I really only care about labeling this one in this case. And all the others I want to treat probabilistically. I want to kind of average out over all the possible assignments of everything else in the sentence, taking it all into account. What would I choose for word 3 in this case? Is it clear how this is a little different? Now's a good time to complain if it's not. This is not a complaining crowd. Okay, so just kind of an aside. Probabilistic graphical models, really useful framework for machine learning and NLP, and really complementary, I think, to deep learning and neural networks. They are depicting something different in the graph than what you see when people draw neural network architectures. These are showing you not the calculations, but rather the commitments you've made, the independence assumptions that you're choosing when you design your model. HMMs are one simple kind of graphical model. There are many others that build on this idea of putting a semantics on the edges between the nodes. Bayesian networks, Markov networks, factor graphs, big thing in Andre Martinez's thesis when he was a student was factor graphs. These are really useful if you want to reason explicitly about the different kinds of assumptions that your model is making. But today we'll just stick with the HMM model, which has this nice simple chain structure, and focus on what it means to color different nodes red and blue. So sorry, there's some math on this slide. What I'm interested in here is finding the most probable label for the ith word, marginalizing out labels for all the other words before and after it. And what the mathematical expression on the slide is showing you, okay, notice joint probability of all the words together with particular state SI. This is hiding a sum over all the assignments of all the other possible states from 1 to I-1 and from I+1 up to N. I want to sum up over all of those. because of the independence assumption of the HMM, I can split that into two parts. There's the probability of the states up through I that came before, and the probability of the states I plus 1 through n that came after. And because I could decompose that into two probabilities, and neither depends on the states that the other depends on, I can then move the sum inside and recognize from, if I remember all of the things I did earlier in the lecture, which I don't expect you to exactly be able to match this. Essentially, this first sum is the forward probability up through state I, and the second term is the backward probability up through state I, back up to state I. And so basically, if I want to choose a particular value for state I can score it by multiplying together its forward and its backward probability. And if I renormalize these two things together, I get the posterior over state I taking a particular value, being assigned a particular label. So the algorithm for getting this, for if I care about just one particular word, is to run the forward algorithm up to that word, the backward algorithm up to that word. Sorry, I did that backwards. I need to remember how to switch. So the forward algorithm from the beginning up to word I, the backward algorithm from the end up to word I can stop there. And then I essentially take a kind of inner product and renormalize to get the posterior distribution over what label this particular state should take. And an interesting kind of aside is that the denominator, when I renormalize this is just an alternate way to calculate the marginal probability of the word sequence. When I did the forward algorithm, I basically started at the left and went all the way to the end. When I did the backward algorithm, I started at the right and went all the way to the beginning. Another choice is to do forward up to a point, backward up to that same point, and then take an inner product. And any of these will should give me the same marginal probability. So if what you care about is the distribution, the posterior distribution of labels for one particular word in the sequence, you don't have to invent anything new. You can reuse the quantities you got from the forward and the backward algorithm. Okay, kind of interesting. I don't know, maybe you can imagine a use case. I can imagine use cases for this. We're going to build on this and come up with kind of some interesting alternative ways to decode, some alternative ways to label the sequence of words. So before, we assumed that the thing we wanted was the most probable total full label sequence given the words. Here's an alternative way to decode. And I want you to think about why I would choose one or the other. So imagine that I run the forward and backward algorithms. Okay, I take my sequence, I have my HMM, I run the forward and backward algorithms, and now I have these distributions over the state at each position I by taking products of forward and backward probabilities at each position, and then I basically just choose the max of these for each position. So in other words, each word is getting its own label based on all of its forward and backward probabilities. Or another way to say it is that I'm choosing the maximum a posteriori label for each word, independent of all the other words. All the other words have been marginalized over. This has a name. It's sometimes called posterior decoding, as opposed to the Viterbi approach. And it's kind of an interesting alternative. It's using the whole distribution over all the alternative positions in the sequence to make a choice about word I. So mathematically, I don't know, once you have the forward and backward probabilities, you can think of this as completely independent. This might remind you a little bit of the predictions that can be made by a masked language model, where you mask some inputs and then try to predict things at given positions. It has a sort of similar computational property in that each of the decisions is independent of the other decisions once you have the quantities. Very different from Viterbi, where everything depends on everything else, right? You need a globally good sequence that maximizes the total probability of that sequence. Why would you pick one or the other? This is the kind of question that we used to keep ourselves up at night over, wondering, when you have a model that's so powerful and can calculate so many different quantities, why would you choose one or the other? The answer will not be empirically one always works better and the other always works worse. It's not like that, unfortunately. These models make so many assumptions, and they're trained to do something that's quite different from what you ultimately want out of them. So you can't really expect that like there's some philosophical reason to choose one or the other. That there's some empirical reason to choose one or the other. There's maybe a better way to look at it is that they're both actually solving the same problem, but with some slightly different choices. And so I'm going to try to unify them both. There is one interesting point I want to make about the posterior decoding approach. It doesn't necessarily give you a label sequence that has positive probability. It might actually choose something that the model thinks is terrible. In a certain way, it's sort of empowered because each word can make its own decision, taking into account all the options for everything else. You might end up making a decision for two adjacent words that makes no sense even under the model on its own, because the probability of this label following this label is 0. Kind of interesting that can happen. And whether that's good or bad really depends on your problem and your data. Anyway, let's try to unify them so that you can think maybe in a broader and more enlightened way about decoding in general. Okay, here's what we're going to do. We're going to introduce a notion of cost. We're going to imagine that we're gambling. We've constructed our HMM, and now we're going to play a game. The HMM is going to be given a new sequence W, and then we're going to use the HMM to label it. And our label sequence is then going to be compared to the true one. Call that S star. This should feel familiar. It should almost feel like we're running our test time inference to evaluate how well our algorithm works in a machine learning, to decide whether we can write a machine learning paper about our new model. But instead of writing papers, we're going to make it more interesting. We're going to pay a fine if we do badly. You're going to lose money. And of course, your goal as the builder of the model is to minimize the cost. Okay, so my point here is that a lot depends on what it means to do badly, right? How are we going to define the cost? Like you have to ask now, all right, so how does this fine work? Tell me more about what it means to do badly. And I think it's really healthy to think about this really carefully when you build NLP systems. What are the ways things can go wrong and how bad are they? And that should actually influence the way you design your models and the way you train them and the way you decode with them. So anyway, my point is our strategy is going to depend on how that cost is defined, how that cost is structured. So we have to start thinking a little bit like accountants and saying, what are the costs? So here's one cost I could have chosen. If I'm your adversary, I could say, well, it's all or nothing. If you get the sequence wrong at all, if it's not a perfect exact match to S star, you pay me €1. If you get it perfectly right, you pay nothing and you can walk away. But you owe me €1 if you make any mistake at all. What should you do? How should you place your bet? If you believe your HMM, if you trust your distribution over words and states, then the answer here is that you should use the most probable whole sequence S. You should ask your HMM, I only get one shot. I have to choose a full label sequence and I have to get the whole thing right. What's the best choice? And it's going to say, run the Viterbi algorithm, and I will tell, that will tell you what my most probable whole sequence of S is. Provably, right? I sort of showed you the proof. You should sort of believe it. All right, that's the all or nothing cost. The Hamming cost is different. This is an alternative. So start over, different take. Suppose that I tell you what's going to happen is every word you get wrong, you're going to pay €0.1 of €1. But the more mistakes you make, the worse it is for you. But it's much more forgiving. If you focus on reasoning about each word without worrying about the coherence of the whole sequence, that might actually be a better strategy here, because the goal is to get as many words right as possible. It doesn't matter as much to get the whole thing. Obviously, you want to get the whole thing right? The best answer here is still the same as the best answer with the all or nothing cost, but it's a little more forgiving, and maybe there's a different strategy. And in fact, you can show that if you trust your distribution, if you believe that you have a really good model, then you should use the most probable, let's just say the most probable label for each word. So you should use posterior decoding and choose each word's label so that your bet on that word is least likely to cost you any money. Okay, I'm not going to give you the mathematical proof that these are the choices you should make, but hopefully it's intuitive to you that the way you should decode depends on the way the errors will be held against you or what you're going to have to pay for different kinds of errors. So the general unifying principle here is something called minimum Bayes risk. The assumption that you have a good, well-estimated distribution over your outputs leads naturally to this general decoding rule that says you want to choose the S hat, the label sequence, that minimizes the expected cost, where you treat the true label sequence as being modeled well by your model's distribution. So this P here in the expectation is your model's posterior. So pick the S that is least offensive in expectation, but least offensive depends on how you take offense. It depends on the cost. So if the cost is all or nothing, you should use map or Viterbi decoding. If the cost is Hamming cost or per word cost, you should use posterior decoding. Different strategies depending on how the errors are structured. Interestingly, if the cost function is any kind of sum of local costs, then you can make use of this kind of same trick that posterior decoding gives you, where you use independent decisions once you know how the local costs are structured. So if, for example, some words count more than others and have a bigger cost, that might lead you to use this kind of posterior decoding. Or if some kinds of errors are way worse than others, you might weight them appropriately using this kind of approach. So this leads to kind of an interesting, another interesting tangent, kind of like, one of the things I like to notice earlier was that the semi-ring was sort of a choice you could make that might lead you to different kinds of algorithms. Here, changing the cost function might lead you to totally different ways to decode. We talked earlier a little bit about named entity recognition, and I pointed out that when people use HMMs for these kinds of sequence chunking or labeling or segmentation tasks, they use BIO tags. So mark the beginning of a chunk that you care about, mark the insides, maybe add a label to those like name of a person, name of a place, outside, O for outside, meaning it's not part of one of these special chunks. When you do this, when you solve this kind of problem, there's often a trade-off between precision and recall. Do I want to make sure that all the chunks I choose are correct, or do I care more about finding as many chunks as possible at risk of maybe getting too many and having good recall but low precision? Are people familiar with precision and recall trade-offs? Have you heard this before? I'm seeing some nods. It turns out that if you care more about recall or care more about precision, you might change the cost function without changing your model, without retraining, which is something you could do. You could retrain your model to get a higher precision, to trade off between precision and recall if you care more about one or the other. But an interesting thing you can do once you fix your model is you can change the emphasis on precision or recall, or turn a dial between the two and get different output that maybe makes a different choice in that trade-off. So this is kind of, don't look too closely. This is basically saying, if I were doing BIO tagging and I cared more about recall or precision, I might score different pairwise errors about the B, I, and O tags, depending on whether they correspond to merging two entities or splitting an entity that should be one thing, or a precision error or a recall error or a boundary error. I kind of categorized all the possible pairwise mistakes this way. So this leads to a different kind of posterior decoding, where I actually want to look at every pair of adjacent states and measure the cost based on the kind of mistake I made for this pair. You can do the same thing. The slide shows how you pair up the different forward and backward probabilities with other model components. This involves running the forward algorithm up to I, the backward algorithm up to I+1, multiplying in the things that would need to happen in the middle to get posteriors over pairs, adjacent pairs of states. This is what it looks like as a graphical model. I think this is a little more clear, hopefully. You're choosing the red values, two states at two adjacent positions, while summing up over all of the states that came before and after. An interesting twist about this kind of pairwise decoding. By the way, I've never seen anybody do this in a paper, right? What I'm doing now, it's kind of like, stupid pet tricks for HMMs, right? This is something that falls out very naturally once you have a full understanding of the quantities that you're calculating. It's an interesting thing you can do. You might find a use for it. I don't know if anybody ever actually did. But if you understand the points that I'm making, then you can be confident that you have a pretty deep understanding of what these things are capable of, and you might find that you can put them to new uses. In any case, this kind of pairwise decoding is a little weird. It basically says for every adjacent pair, I can come up with a pair of labels independent of all the others. But the problem is the pairs overlap, right? The pair at 4, 5 overlaps with the pair at 5, 6. So how do I make sure that those two choices of pairs of labels are actually consistent with each other? There's nothing that guarantees that they will be. So here's the solution, and it reuses everything we've seen in the lecture. First, run forward and backward. That's your pre-calculation. Then use the posteriors to score all possible label pairs for all adjacent words with their expected cost. Okay, so now I know what it would cost me if I make this particular choice and the probability that my model would assign to that error for every adjacent pairwise choice. The last thing I'm going to do is find the best scoring consistent labeling. And it turns out I already have an algorithm for doing that. It's Viterbi, but I have to change the semi-ring. I have to use a min-cost semi-ring because I'm trying to minimize the expected cost now, not maximize a probability. So I change the semi-ring. Now my values in my Viterbi algorithm, they're not transition and emission probabilities. They're these expected cost quantities that I got out of forward and backward probabilities in my cost matrix. And then I run the algorithm and I get back the expected minimum cost weighted by posterior probabilities, so the local risk. Yes, this is very contrived, right? I basically just gave you a single approach to decoding that may not actually solve a problem you really truly have, although I can kind of imagine you might have a problem like this, but it uses everything we did in the lecture up till now. It puts it all together in one place. So anyway, higher level point is with this kind of model, with a generative model like the HMM, you actually are empowered to be creative about your cost function and to choose how different errors might affect your decision making when you run the model. The model, unlike today's models, which are trained to just give you an answer, these models you can run different inference algorithms and get different answers depending on what you really care about, your cost function. So here's another pop quiz. Try to think of a cost function such that you could not use the tricks I used. The minimum Bayes risk decoding would not be polynomial time possible because of the structure of the cost. And I'll just remind you, the thing I exploited was that the cost factored into local errors, either at a single word or two adjacent words. Can you think of a cost function that doesn't look like that? You get to be the adversary now. No ideas? Yeah, no, that was just scratching it. Okay, I won't torture you. Here's an answer. Every word has to get a different label. You pay if you reuse a label. This does not decompose nicely. It now makes every word's cost depends on every other word. Every label must be used exactly once. That's kind of it's a weird cost function. I can't imagine a specific NLP problem where this would come up, but maybe you can. This basically relates to Hamiltonian paths. If you remember your suite of NP hard problems, probably no efficient way to decode this one in polytime. Okay, so you can be evil with cost functions if you want to, but I think they're also an interesting source of creativity in in harnessing your model to do different things for you and to solve different tasks. Okay, how are we on time? We have until 12:30, is that right? So we have time to talk about learning. Okay, you came to Lisbon for machine learning. Let's talk about learning now that we're almost at the end. So learning in HMM, really, usually people talk about it as learning the parameters, learning the gamma and the eta. And that comes in two flavors. You might have states and sequences, or you might just have, oh wow, this typo has been here for years, or just sequences, not just states. I don't know why you would ever have just states. Strange, I have to fix that. Okay, so let's talk about learning algorithms. One of the other things that's kind of important here, and is sort of, there's a whole sort of side literature we could talk about and won't, is what if you don't really know what the states should be or how many states your HMM should have? That kind of kicks you over into a different world. We're going to assume today that you know how many states you have. Maybe you have some constraints on the states that would disallow certain transitions, or that would make other interesting dependencies among your choices. We're going to leave all that aside for now. We're just going to assume it's kind of a basic HMM. And we have two possibilities, and these are usually called the supervised and unsupervised case. So the supervised case, you get examples of words with their states, you know the labels, it's labeled data, and you can estimate the parameters by doing supervised learning. And the second one is you only get sequences of words. You never see states. And this is actually the traditional one. This is the one that gave HMMs their name. The assumption when HMMs were invented in the 60s was that the states would never be seen. They were something that you only inferred by doing unsupervised learning. There is a sense, I think, in which the roots of today's neural representation learning, where you take large amounts of raw text and build language models on it, has its roots in things like unsupervised HMM learning, where, again, you only have words. They were not working with the scale of data we have today. They didn't have that scale of data, and they certainly didn't have the compute to do unsupervised learning on it. But in some sense, the shape of the problem is the same. You get these words and you're trying to infer something from them, a useful representation you can use. In this case, the representations are the state sequences. They're discrete. But I think there's some interesting connections to what we're seeing now with neural models. So the supervised case is super, super easy for HMMs. Everything in an HMM is a multinomial probability distribution, right? Distributions over the next state, given the current one, or distributions over words in the vocabulary, given the current state. Statistics tells you when you have probability distributions to estimate, you can use the maximum likelihood principle. Choose the probabilities that maximize the total probability of all of your observed data. And because of the observations, the fact that the data is totally observed, it lets you estimate the transition and emission distributions completely separately from each other and per state. So learning is very simple and fast. There's a closed form solution. You count up the number of times you saw each transition, divide it by the number of times you saw, this should be sigma prime. That's 2 mistakes I found in the lecture. I don't think I've ever had a year where I found 2 mistakes after the first one. For the emissions, you take the frequency of the state and the word and divide by the frequency of the state. This is usually very intuitive, but there's also a proof that this is the maximum likelihood solution that I'm going to skip. It involves a little bit of calculus. But it's a fairly easy proof that these are the maximum likelihood estimates. You don't need backprop. You don't need any fancy neural net packages. You literally just count and divide. Maybe you do a little bit of smoothing to make sure that you don't have zeros if you're worried you don't have enough data. The graphical models view of this is kind of cute. Here I'm showing you using the same notation we had before, except that I've now lifted up the parameters, the gammas and the etas, to being additional parents in the model. I'm treating them as if they were random variables that I'm trying to estimate values for. So the states depend not just on their predecessor, but also on the choice of parameters gamma. The words depend not just on their corresponding states, but also at the bottom on the emission probabilities eta. I've colored those parameters red because I want to select them. I want to maximize over them. It's called maximum likelihood. I want to choose the values that make the observed data, now states and words, I'll color gray, as likely as possible. I'm reusing the same visual notation because I think it gives us an interesting way to think about what we're doing when we learn parameters for a model. Learning parameters and doing inference are not necessarily so distinct, although the algorithms we use to do them are quite different here, right? No, there's no forward backward, there's no Viterbi, there's nothing fancy, no dynamic programming. You could probably do this in 5 minutes in Python. This is maximum likelihood estimation. I like to contrast it with learning with a prior. If you have lots of data, this is going to be great. You don't need to worry too much, but we never have as much labeled data as we would like. This is a recurring theme in the history of NLP. If you want to do supervised learning, you are probably going to be limited in the amount of data you have. And so you want to make the most of the data you have. Often a way to do that is to inject some kind of background knowledge or prior knowledge into your learning and avoid overfitting to the training data. This is probably familiar to you from neural nets. The probabilistic answer to this is something called maximum a posteriori or map learning, where you are maximizing not just the probability of the observations that you have given the parameters, but also the probability of the parameters themselves. And I'm going to give you the dead simplest version of this prior, the probability distribution over parameters. Because they're built out of multinomial distributions, we want something that's really easy to work with multinomials. And the simple answer to that is something called the Dirichlet. A Dirichlet distribution is a probability distribution over multinomial distribution parameters, or over points on the unit simplex. And the simplest version of this is symmetric and non-sparse. So in practice, what it means is for every transition distribution, we're going to have an alpha sub t. For the emission distributions, we're going to have alpha sub e. And these are just values that are greater than 1. For historical reasons, we set them greater to 1. We subtract 1, so we get some value that's positive, and we add it to the transition counts. Similarly for the emission counts, it's like a pseudo count. It's like saying, I'm going to pretend, because of my prior knowledge about the world and about HMMs and about language, I'm going to pretend that I've seen each of these transitions and each of these emissions a small number of times more than I've actually seen them. And that small number could be 1, it could be 0.1, it could be 100. It's your choice. Depends on what you believe about the world, but you choose this positive value and you basically augment every transition and emission count with that value before you renormalize. It's exactly the same as additive smoothing in language models, but we're just applying it to HMMs. Graphically, you can think about it as putting another gray parent node on top of your red nodes in this little graphical model. This is taking the graphical model thing to a very strong extreme. Graphical models, people would probably laugh at me right now if they saw this, but I still think it illustrates the point really well that you're adding in some additional information about where these different parameters came from. Okay, that's all I'm going to say about the supervised case. The supervised case, again, was not where these things originally were invented for, but we did use supervised training for HMMs quite a lot in NLP in the 80s and 90s. And then things started getting more interesting, and there were really 2 branches of work around the year 2000 that were really active building on these HMM foundations. One was to take the supervised learning thing and make it more powerful by using features. That's where things like conditional random fields came from, kind of using more modern machine learning techniques to reparameterize the models, train them discriminatively. Structured perceptron was another technique. These were things that used to be covered in some of the more advanced lectures here. The other branch, which I think is a little bit more intellectually related to what's happening in the field today, was to go toward unsupervised learning. And again, the roots of HMMs, you did not observe the states. They were hidden. That's why they were called hidden Markov models. The Markovian nature of the data had to be discovered by estimating the parameters of your hidden Markov model. And this goes back again to the 1960s. The first unsupervised learning method for HMMs, which I will show you now in my notation, was called Baum-Welch training, and it was invented in the mid-60s. Okay, and I think this is also the earliest instance of estimating the parameters of a probabilistic model where you don't have complete data. The idea that I'm going to show you was generalized in the 70s into what's known as the EM algorithm, expectation maximization algorithm. So I'm going to give you the HMM version of that. So we only get words. We've never observed a state sequence. How do we learn the distribution over state sequences given that we've never seen one? The tools that we need, we've already seen. This lecture is great to teach because whenever we get to something really hard, it turns out the tools that we need were already given to us earlier in the lecture. So there was a little bit of method to all of that math. From a statistics point of view, we're still going to be trying to do maximum likelihood estimation. We still want to choose parameters that make the data as likely as possible. This principle is still pervasive today, even with neural language models. We still use maximum likelihood estimation there. For these multinomial-based things, that means we're going to be counting and normalizing some things. From a computational point of view, we're going to be doing that, but we're going to be doing this in a sort of soft way, using posterior distributions. And so the tricks that we need there are going to build on the forward and backward algorithms. So you have all the tools. This is our statement of the problem. We want to estimate the parameters, the gammas and the etas, which are red, like we did in the supervised learning case. But we don't observe the states, they are blue. We want to sum them out. We want to marginalize over all possible values of the hidden states and make the probability of the words as likely as possible with our choice. There's red and there's blue. This is called a mixed inference problem because we're trying to maximize over some things and we're trying to sum out others. We saw some instances of mixed inference earlier when we did posterior decoding. There was red and blue on the slide at the same time. That was solvable efficiently. But in general, when you have both red and blue, the problem is hard in general, NP hard in the most general case. And so in general, this problem of finding the maximum likelihood estimate is NP hard, and you cannot hope to do it exactly. So from an optimization point of view, we're doing something that as soon as people figured it out, they got very nervous because it's really hard. We're optimizing a non-convex function. The likelihood surface with respect to the parameters of the HMM is not convex. This should make you shake and shiver and be scared, but it doesn't because today we do this all the time. Every time we train a neural network, we're trying to optimize a non-convex function. Times have changed. When people were doing this, even 15, 20 years ago, there were people who wouldn't touch this problem because they were not comfortable with the non-convex loss surface. Totally different now. Now, when you see a convex problem, it's like, oh, this is so quaint. Like, this can't really work for anything. It's convex, haha. But it used to be very different. Now, like I remember telling like senior people in the field, I'm trying to do something with unsupervised learning, and the loss is non-convex. I don't know about that. No guarantees. Anyway, the EM approach is kind of a beautiful thing because it takes that mixed problem with both red and blue and decomposes it into two different subproblems, each of which is totally reasonable. And in fact, we've seen them both. Okay, so the EM stands for expectation maximization, and it also tells you how the algorithm decomposes into parts. On the left, we have the E step, which is infer the posterior distribution over the missing data, leaving your parameters alone. Just fix them from the previous round and contemplate the distribution over the hidden states in your training data. Then on the M step, we're going to maximize likelihood with respect to the values that we chose for the missing data, but we didn't actually label the missing data. Instead, we have soft distributions over the labels at every position, and we're going to use that posterior distribution to sort of softly impute everything that's missing in the data and estimate the parameters to make that distribution as likely as possible. And we alternate between the two. So here's the procedure. Start off by choosing parameters for the HMM, usually something close to uniform with some noise. If you have some intimate knowledge of your problem or some prior way of choosing the parameters that injects some knowledge in, that's not a bad thing. And then you iterate. On the E step, you calculate the probability of every possible transition and every possible emission at every position in your data. That sounds more daunting than it is. A lot of that computation is going to be shared because the forward and backward algorithms do most of the work. And then on the M step, we re-estimate the parameters to maximize the likelihood of this now softly completed data. I'm going to talk about each of the two on its own. In math terms, the E step is calculating the probability of the state sequence for every state sequence that you could choose. But we're not actually going to enumerate those. That would be way too expensive. What we're really going to do is calculate for every word position the distribution over the state that word is getting, and count softly each of the emissions of that word at position I from each of the possible states proportional to its probability. So it's like, instead of saying this word was generated by label number 43, we're going to say this label was generated by from label 43 with probability 0.7 and label 45 with probability 0.2 and so on and so forth for the whole thing. We're going to fractionally count each of the possibilities. And we're going to do the same thing for these pairs of labels so that we can get soft counts of each transition. You may remember this quantity here, the single label probabilities from posterior decoding. And you may remember this one from that weird 2-label second version of posterior decoding that I sort of contrived to force you to look at these weird posteriors. Both of these you get from the forward algorithm and a little bit of algebra. So you do the forward and backward algorithms. You obtain all of these posteriors. Then you're going to treat them as soft or fractional counts of transition and emission events. Here's the math. Everything boils back down to the forward and backward probabilities, and these frequency hats, they're like the same as the frequencies we used in the supervised case, but now they're soft. Everything is based on fractional counts based on the posteriors that we get from the current iteration of the model with the current gamma and eta probabilities. Okay, that was the E step at a high level. The M step is just going to take those soft counts and renormalize them. So up above, we have the observed supervised case where we had full data, we counted things, we renormalized. Here, we have the soft counts, the soft frequencies, frequency hat, estimated using forward and backward probabilities. We're renormalizing them in exactly the same way. And you can prove that if those fractional observations were real data, this formula is giving you the maximum likelihood estimates for the transition and emission probabilities. Okay, that's essentially it, the EM algorithm. It is very, if you're familiar with the kinds of SGD, stochastic gradient descent based training we use for neural nets, it feels very similar. We're iterating over the data. We're doing this kind of calculation that's kind of intensive over every instance in the data. We're getting some intermediate quantities. We're updating the parameters with a closed form every round. There are some similarities between EM and gradient descent that are out of scope for today. But basically what we're doing is similar in that we're hill climbing the likelihood surface. Every iteration of EM should give us an estimate with a better likelihood than the last. It will, that's guaranteed. It's actually a little bit better than what you get with gradient descent because you don't have to choose any step sizes. It has kind of an interesting self-scaling property. Eventually, it will converge to a local optimum or saddle point, and we don't usually worry about the saddle points. But what this means is that where you end up and the quality of your solution with EM depends on how you initialized. So, you know, I like to use the analogy of having your friends airdrop you onto some random location on a mountain like Mount Rainier, which is the mountain right outside Seattle. And then you're blind or you're blindfolded and you start using your feet to feel which way to go, and you try to go I guess down. You would probably want to go down if down would probably be better, but either way, you shouldn't be too hopeful about reaching the global maximum or minimum regardless. Either way, you're going to get to something local, and that might be good enough. In neural nets, we generally think that's good enough because we get good performance. With EM, it wasn't always. A lot of the work where people used EM involved clever initialization or doing many runs of EM and picking the one that got the best likelihood, because sometimes you get something not so great. And there are other versions. So people do things, would do things like, instead of using forward and backward, because gosh, that's complicated, all those forward and backward quantities to keep track of, maybe we just use Viterbi and get hard counts. So this hard EM, sometimes this is called self-training. You basically randomly initialize your parameters over on the right, that's your M step. Randomly initialize your parameters, then do an E step, but make it a hard E step where you just run Viterbi and label all the data, then re-estimate the parameters on that and repeat. Sometimes this would work. And you can think about it as doing coordinate ascent on a problem like this, where you're trying to choose the parameters and the states to jointly maximize the probability. Some people liked this better, maybe easier to implement, tended to converge faster, obviously different surface, different function, maybe more brittle. I don't know, it's another option worth pointing out. Using the same principle of decomposing that challenging parameter and latent variable problem into two. Stepping back, this idea of expectation maximization, it's incredibly general. It's applicable to any generative model with latent variables. And likely, if you've seen it before, you saw it for mixture of Gaussians. Has anybody seen EM for mixture of Gaussians? Yeah, it leads to like a clustering, kind of a clustering model. K-means clustering is basically hard EM for mixture of Gaussians, if you've seen K-means. The HMM version of EM is sometimes called Baum-Welch or forward-backward training. These are the forward-backward for the obvious reason that it uses the forward and backward algorithms. Baum-Welch after the people who introduced it in the 60s. I want to just kind of make a couple other connections to ideas in the literature that you might encounter. Who's taken a class in theory of computation? Few people still do this. Okay, good. There's an interesting connection between HMMs and finite state machines, which you may have seen in a formal language theory class, or you may have seen in an NLP class, depending on who was teaching it. They both have like finite sets of states and transitions between the states, and they both can account for kind of non-determinism in moving among the states. And the states in both cases generate symbols. So you should feel like HMMs are kind of like a probabilistic finite state machine. They just replace the non-determinism with a well-defined probability distribution, both over the states and over the words that are generated. Both of these can be generalized more powerfully into something called a weighted finite state transducer, where you can, instead of thinking of just like generating a language or generating a set of strings, you can think about mappings between strings to other strings, or relations where you read in one tape and you write out another. And you can make these probabilistic. And there were really interesting things you can do when these are formulated as finite state models, where you could compose different relations or chain them together and do string to string transformations in a bunch of different ways. And all of this could take advantage of the kind of efficient techniques for inference and learning that we saw in this lecture. Today, these have been more or less replaced by sequence to sequence approaches, right? So you have models that read in a sequence and encode it in some kind of usually matrix, and then generate outwards, right? And decode outwards into a sequence, usually from left to right, maybe with beam search. There's some interesting relationships between these newer approaches and the older ones. But the older ones had something that we don't have with the new ones, which is that you could decompose them into parts, you could inspect them, you could learn them in a factored way from different complementary data. And people used to do things like build speech recognition systems where they would first map acoustic signals to pronounced phonemes and then to words. And you might think of this as a pipeline. You could also think of this in a more probabilistic way and marginalize out the intermediate step. And they did the same thing with translation. Words in two related languages can sometimes be translated more easily if you first decompose the words into morphemes. And then if you have a very closely related language where the morphemic transformations are really predictable, like I'm told Czech and Slovak, then maybe translation between these could be done entirely just through morphology. Anyway, that's kind of an interesting connection to some formal computer science. All of these kind of finite state models, HMMs and their friends in finite state world, had versions where the probability parameters were replaced by feature weights. And there was all kinds of learning that was done where these things were transformed into problems that were solved with spectral methods or neural networks. There are discriminative training approaches. If you've heard of conditional random fields or max margin Markov networks, these originated as essentially HMMs, but trained with discriminative criteria. And if you look at the methods that are used there, they look more and more like the methods we use for the SGD type methods we use for neural nets. People started playing with the independence assumptions. They would make weaker independence assumptions among the states and get semi-hidden Markov models. They came up with other estimators that didn't require the kind of iterative approaches we saw with EM. So spectral estimation was a hot thing for a while. And all of this was generalized to more powerful models that made weaker independence assumptions among the sequence, the elements of the sequence. So beyond, if you look at this from a theory of computation point of view, the next thing beyond finite state methods is context-free grammars. And there are probabilistic context-free grammars. There are weighted context-free grammars. There are discriminative versions of these. All of these things were intended to model more long-term interactions among a sequence of words, which is what we find in natural language. Also reordering, if you're doing translation, if you're trying to solve translation problems. And then there were Bayesian versions of these things. So I gave you a little taste of that when I introduced priors for doing supervised learning of HMMs. But you can do that in the unsupervised case, and some of the priors got really fancy. There was something called an infinite HMM, where you made no assumptions at all about how many states you would need, and instead let the data work out how many states would actually make the most sense for your data set. Okay, quick point about the connection between HMMs and neural nets. Neural networks for sequences can do things that these models can't. Okay, they are more powerful. The latest models are much more powerful, and that's like not very controversial to say. But there is a really interesting question about what are those differences? How do we characterize them? How do we say more formally what it is that the new models are able to do that the old ones couldn't? And also, I think there's not much to say about this at all. How do we characterize what they actually learned that the old models couldn't have learned under any circumstances? So I like to point to a little bit of theoretical work that came out of my group over the past few years. We introduced an abstraction called rational recurrences. This was before transformers completely took over. So we have nothing to say about transformers at this moment, but basically we could come up with recurrent neural networks that can provably be reduced to weighted finite state machines. Okay, so putting them kind of in the same family as HMMs. And interestingly, once we proposed this idea, we found a whole bunch of neural nets that people had proposed as alternatives to the very popular LSTM that had this property, that were rational. People had already been inventing rational recurrences before they had a name. And then we went on to find kind of more theoretical things about like hierarchical relationships among the capabilities of different kinds of recurrences. And I think with a little bit more time, and if some of my co-authors keep going in these directions, we'll start to see some characterization of what transformers are doing or different versions of transformers are doing and what they're capable of that other models weren't. It tends to be the case in NLP, and I think all of computer science, that people come up with things that kind of work, they work well, we keep using them, and then behind them, usually a few years later, others come along and try to understand theoretically what was going on. And sometimes we get really nice insights by doing that theoretical work, so I'm hopeful. All right, I think that's it. And we're done a little early. I must have had extra coffee this morning. You didn't ask it, that's what happened. The lecture evolved every year based on the questions I got the year before. And you guys asked a lot less questions than I've been getting in the past few years. So it's your fault, not mine. Ask me questions, let's use up the time.
First question. You briefly touched on conditional random fields and max margin Markov networks. Could you maybe elaborate a bit about the difference between the two? Because like H&Ms and CRFs, they're built on very probabilistic foundations.
Yeah.
Max margin on the
Yeah. So this is a great question, and it wasn't actually immediately obvious when these papers came out that they were so similar. But if you think about the CRF and the chain structured maximum margin Markov network with the same independence assumptions and the same features, they're almost the same up to the loss function. Basically, one of them is using kind of this soft log loss type thing, and the other one is using this like harder hinge type loss. And I think actually Andre, who you all know now, had a nice paper with another student of mine, Kevin Gimple, in like maybe 10 years ago, that showed that these were two instances of a larger family. And really, like a lot of things I showed in this lecture, like you squint in the right way and you use the right notation, and suddenly the things that are known and familiar and you thought were totally different are really just two members of a bigger family. That's the way I think about those two. There was never really, in my mind, compelling experimental evidence that one of these was better than the other. In terms of performance. It was more like if you wanted to avoid doing summing, which sometimes you really did. Sometimes the summing algorithm isn't so closely related to the maximizing algorithm. The max margin network was really appealing because if you could maximize, then that's all you need, both for training and for inference. If you really wanted probabilistic quantities and probabilistic interpretations, the CRF obviously was the way to go. But they're so similar. And if you actually visualize the loss functions, it's like one of them has a hard elbow and the other has a softer elbow. It's like SVMs and logistic regression. They're so close that it ends up being practical reasons to choose one or the other, not so much religious commitments. That was where I landed. It's funny, we don't really see people using like margin type losses or cost infused learning for neural nets, but we could totally do it. We could use, and the nice thing about the SVM, the SVM and the max margin networks was you could take those loss functions that I was talking about, and if they factorize nicely, you could put them into the learning and you could guide your model towards a better solution given your cost function. Don't see that very much now. There's one in the back.
Hi, and thanks for the talk. I wanted to ask if you have maybe anything to say regarding the maybe links between capacities of these models and the language hierarchy, like the Chomsky hierarchy, different families of languages.
Yeah. I mean, this is like very classical computational linguistics question. I guess, there's this long-running debate that was more or less settled in the 80s about where natural language fits in the Chomsky hierarchy. And then there's sort of like, you add weights or probabilities to things and you get a whole new set of questions about what, does that change things? Like once you have probabilities, maybe learning becomes easier and that may reflect on the human language capacity. And there's people who could talk about this all day, and I think it's all very interesting. I think the thing that those debates tended to miss in NLP was that we always have finite data, and just because the formal representation more elegantly captures all the phenomena, it doesn't mean you're actually going to estimate it well with the data. So like there were extreme positions taken by some people that like, well, maybe you can more elegantly explain natural language with some fancy grammar than with a finite state model. But the finite state model is actually going to do really well in the majority of cases if you have enough data. And so maybe we should just like focus on that. And, you know, there's another point that like, well, the things that are used to argue for those really fancy grammars don't actually happen very often, if at all. Like there's only so much nesting even speakers of Swiss German can handle. So maybe, you know, maybe this is so far at the margins that it's not that important. I think right now, for me, the more interesting question is, are there any limitations at all being placed by the models that we use today? How would we characterize them? Are they helpful? Are there ways to impose better biases on them? I mean, this is something that you won't hear most machine learning researchers talk about, is the importance of inductive bias in learning. You cannot learn to generalize without some kind of inductive bias. No matter how proud people are of the new architectures and how well they, you know, how much incredible capacity they do have inductive bias. We just don't understand it very well. We don't have language for talking about it. And my suspicion is that one of the ways we're going to get better models that are less expensive and can generalize better from fewer examples is to think about inductive bias and come up with better formalizations. I think the old ways of talking about inductive bias, the Chomsky hierarchy and so on, maybe they'll give us some inspiration, but I don't think we should be locked in on that as the right set of tools. We're in a different world now, and maybe those are not the right abstractions. I think there are probably millions of others we haven't thought of yet. Great question, though.
So, first question myself. I was wondering how would you treat such models to work with polysynthetic languages?
Which models, HMMs, to work with polysynthetic languages?
Yeah, like, I mean, would you see like in addition when you have like a polysynthetic language, like what would you actually do about it?
So I would tokenize like crazy into small pieces, and then I would use a very high order Markov model and hope for the best. That's the best answer I can get. I don't know what else to say. That would be really hard. I haven't worked with polysynthetic languages, but my understanding is that they've got crazy morphology and lots of long range dependencies. And so this would probably not go very well. I'm not sure neural nets would be much better. Like we have no understanding of the kinds of long range dependencies that a neural net would capture in that case either. But there are probably advances in the symbolic modeling of those languages that I haven't learned about, like using optimality theory or something like that. And maybe, there was this, that's just a wild shot in the dark. I really have no idea, but there was a really interesting line of work called primitive optimality theory, where people were encoding the constraints in optimality theory with finite state machines, and then putting them together into more complex machines that could like manage all the constraints. Interesting stuff. I haven't seen it in 20 years though. Yeah, maybe there's something to be done. I don't know. Polysynthetic languages are also hard because for most of them, there's probably very little data. Yeah. Yeah, I will say though, there's one topic I still teach in my NLP classes where when I cover morphology, I spend like one lecture on finite state morphology. Not because I think finite state machines solve all of morphology, but just because as far as I know, that's still the best way to model morphology is to hand build a finite state transducer. And it gives you decomposability and it lets you capture lots of different phenomena. And there's no better way. If you care about morphology, there's just no better way that I know of. And like sometimes the solution, I know this is shocking, is not a neural net. And so it's good to know something about a couple other techniques. And that's the one place where I don't think people have better solutions. I don't know if they work for polysynthetic languages then, probably not. Yeah.
Hi, thank you for the talk. I was wondering if you could maybe briefly explain what semi-HMMs are.
Yeah, I can briefly explain. So in a semi-HMM, there's different ways to do it, but the way I remember is like when you get to a state, you don't just decide what word to emit. You first decide how long are you going to stay here? And how many words are you going to emit? So basically it creates like kind of a, like now that you've chosen to stay in this state for a while, now the timing of the length of the Markov dependency is sort of variable in a very particular way, but it's still a very parametric model.
And are there particular contexts where they would be useful as sequence models?
Yes, I remember reading a survey paper about this. And I think most of the cases were not NLP, but maybe it might have been like audio processing or maybe some comp bio domains where the states had kind of a different meaning. You could maybe apply them to like chunking problems in NLP, and probably people did. I don't remember how well it worked, but yeah, I guess we used something like a semi-CRF with a neural net in around 2014, and I think we were looking at maybe it might have ended up being useful in speech processing. Yeah.
Hi, thanks again for the lecture. This might be a rather specific question. So when we were talking about decoding with HMMs, you mentioned this if you trust our distribution.
Yeah.
I was just a bit wondering what would that be?
Yeah, so I mean, speaking practically, you should never trust your models or your distributions ever. Because they were trained on finite data that probably had biases and whatever else. So there's sort of this tension in any machine learning based research where it's like, well, what guarantees can you offer? And I think the current generation of students is very comfortable with this world where there are zero guarantees about anything and everything comes down to empirical measurements. And you should be skeptical of any guarantees anybody offers you, because usually they're based on assumptions that you can't actually make. So I was trying to be clear about the assumption. These kinds of decoding techniques, the guarantees they give you are contingent on the model distribution being reasonably close to the truth. If the model estimated a terrible distribution, you shouldn't actually expect any of this to work at all. And how good or bad you should feel about that sort of depends on your level of trust in the quality of the distribution that you've got. Maybe that's why we don't see a lot of sort of inference tricks and decoding tricks, but we used to see more of it, and it did make a difference in some cases. Like I remember in one experiment we were doing semi-supervised learning, and we changed the loss function when we estimated the model so that we would bias towards recall, and it had a huge effect. You went and labeled a bunch of data, and with high recall, you actually learned from the unlabeled data much better. Okay, this is a little old-timey. We don't do that so much anymore. I like to mention it because it's another knob you can turn. But the formal guarantees only go so far, and they're contingent on some things. I think it's good to be honest about that, right? There was a time, like I was mentioning convex optimization, when there were some people who would not touch the non-convex problems because they were so fixated on the guarantees they could get in the convex case. And how could you possibly go about, running algorithms when you don't know what they're actually you have no guarantees about what they're going to produce? Well, we're in a different time. The mentality is very different. I don't think either one is right or wrong. Personally, I was always comfortable running non-convex optimization and dealing with local optima, but I think it's good to recognize that there was some difference there, and that it's not actually completely crazy to say, I don't want to run an algorithm and not have any guarantees about what it does. That's not insane. That's a reasonable position depending on what you're going to end up using that algorithm for. I'd like to reveal that a little bit. Hopefully that made sense.
Yeah, thanks.
Hi. Okay. I have a question about the outcome of the lecture. Is there a reason why we've concentrated so much on the HMMs and haven't covered the maximum entropy Markov models and CRFs? Because from the lecture I took, it turned out that the Markov entropy models were better than HMMs, and CRFs were also better than maximum entropy Markov models. So maybe you can comment on that.
Yeah, I can give you the very short, simple historical reason is that in earlier iterations of this course, the next lecture, usually taught by Xavier, covered exactly those models. And the thinking when we put together the topics for the course was you couldn't appreciate the CRF and the MEM. I actually think you can do away with the MEMM. I never liked that model. It had all kinds of problems. That's they didn't ask me to teach that lecture probably for that reason. CRFs I could talk about all day, but the reason, the thinking was, at least my recollection of the thinking was, you couldn't appreciate those without understanding the HMM first. I don't know if that's true, okay? You probably could understand CRFs without getting into details on HMMs. I think you would be missing something. You'd be missing the intellectual thread that, through the history. I don't know if that matters. So yeah, I don't know. In a future year, maybe they're going to make me cover CRFs. Like Noah, drop the unsupervised learning and cover CRFs instead. I'd probably push back a little bit on that because I think the unsupervised learning has more connections to today than the CRF does. And the CRF, it's like, it's kind of complicated. It uses all the same things. It uses the forward and the backward algorithm. You have to get used to features instead of like interpretable probabilistic parameters, but that's not such a huge leap. It's kind of I think of them as like a middle step between the probabilistic generative models and the neural nets we have today. That's the way I teach it at home anyway. But yeah, I mean, I think it's useful to know about CRFs as well. If I had another 3 hours, great, let's do it. I only get 3.
Okay, thank you.
I want to push back on one thing though. You said these other things work better. If all we cared about was how well things worked, we wouldn't teach any of this, right? The HMM is completely dominated by modern techniques in probably almost every setting where we have enough data to consider doing NLP. You probably are not, I don't think anybody's using HMMs to solve any particular problems now. Maybe they kind of are models that have a latent variable that's sort of HMM inspired. No, I take it back. We just put out a paper on arXiv that does do structure learning in an HMM with neural nets. You can put the pieces together. So it's not, I don't want to say it's completely irrelevant, but like just out of the box, you're not going to use this to solve an NLP problem. The reason I think it's worth knowing is to understand the foundations and the principle, like the maximum likelihood principle. You should learn that separate from the neural nets. The idea of inference and decoding as a way of making a hard choice in a very large space, you should learn that separately from the specific models. Learning the HMM forces you to tease those things apart, I think, in defense of HMMs. I heard there was a panel at NACL where some famous professors said they didn't teach them anymore. And it made me very sad. Over my dead body, will I stop teaching HMMs? Maybe not in Lisbon. They might not invite me back. This might be, you may have seen the final HMM lecture in Lisbon.
Okay, so I think we need to go to lunch.
All right, thanks everyone.
Thank you.